2 weeks ago, 3i Atlas made a close pass by Mars, a mere 29 million kilometers away, with an accuracy that was nothing short of surgical. For months, it has been expelling a constant stream of 144 metric tons of water each hour, alongside nickel, cyanide, and ionized plasma. This precise molecular cocktail is the exact recipe for metalloproteins, the very essence of how biology transforms into technology. In just 2 years, Elon's robots are slated to touch down on Mars, tasked with erecting infrastructure and manufacturing new robotic units. Essentially, Mars has just received a cosmic delivery from another star system. The chemistry is flawless, and the timing seems impossibly perfect. What if this entire sequence of events was meticulously planned from the outset? This is a hypothetical scenario, a thought experiment rigorously supported by established scientific principles. However, the undeniable facts remain. If you haven't already, please hit that like button and consider subscribing. In the comments below, share where you're tuning in from, what the current time is in your location, and whether you believe we are witnessing the genesis of a novel life form. To assist our community in expanding, please share this broadcast on X, Facebook, Reddit, or via your messenger. We deeply appreciate your unwavering support. The Cosmic Gardener. What if 3i Atlas is, in fact, seeding Mars? On October 3, 2025, an event of extraordinary significance unfolded in the void between celestial bodies. An object originating from a star system beyond our own, traversing the cosmos at speeds exceeding 200,000 kilometers per hour, skirted past Mars at a distance that most would consider unfathomably vast, 29 million kilometers. For perspective, this is approximately 75 times the distance separating Earth and the Moon. In the immense emptiness of space, this qualifies as an extremely close encounter. However, what distinguishes this particular close approach from all others we have ever documented is that this was not merely a passive celestial body drifting by. It was a deliberate delivery. A user on X articulated this theory with striking directness. 3 Atlas, they posited, is a seed, not in a metaphorical or poetic sense, but quite literally a progenitor for metal-based organic life forms on Mars, potentially heralding the advent of the next generation of intelligent beings within our solar system. Now, before you readily dismiss this as mere science fiction fueled by wishful thinking, let us consider the verifiable data gathered from observatories, space telescopes, and peer-reviewed scientific literature published within the last fortnight. 3 Atlas has been expelling significant quantities of water since its initial detection in July. Not a gentle trickle or a minor leak, but a substantial outflow. The Neil Gerald Swift Observatory recorded this expulsion at a rate of 40 kilograms per second. To translate this into terms more relatable to human comprehension, visualize a fire hose operating at its maximum capacity. Now, imagine that this fire hose has been continuously active since the early summer months. The sheer volume of water involved becomes almost staggering. 144 metric tons every single hour, amounting to 3,456 metric tons daily. This is an amount of water sufficient to fill an Olympic-sized swimming pool each day for months on end. Yet, water alone does not render this phenomenon particularly remarkable. Water is a ubiquitous substance throughout the universe, found frozen within comets, locked away in the icy crusts of moons, and even suspended in the gaseous atmospheres of gas giants. What truly elevates 3 Atlas to a level of fascination, and what suggests its potentially revolutionary implications, is the presence of other elements it carries. In late August, the Kee'ik Observatory in Hawaii directed its sophisticated instruments toward this object. Their objective was to identify the typical chemical signatures expected from a comet approaching the Sun. Instead, they detected something that, according to all prevailing models of natural cometary activity, should be entirely absent: distinct nickel emissions. These emissions were strong, concentrated, and unequivocally identifiable, conspicuously lacking any corresponding iron signature. Reflect upon this for a moment. In the natural world, nickel and iron are intrinsically linked. They originate together from the fiery cores of dying stars, are expelled simultaneously in supernova explosions, and traverse space as an inseparable pair, bound within the same cosmic detritus. Every comet we have ever examined, every asteroid, every fragment of extraterrestrial rock analyzed to date, has exhibited the presence of both elements, albeit in varying proportions. They have always been present, both of them, without exception, until the case of 3 Atlas. This object is spewing nickel at an estimated rate of 5 grams per second, yet of iron there is not a single trace. The research consortium that published their findings in October noted a disquieting observation within their paper. This distinct separation, the emission of nickel devoid of iron, is a known phenomenon. It occurs but exclusively within industrial nickel refining facilities here on Earth, specifically through the carbonyl process. This process involves exposing nickel to carbon monoxide under controlled conditions to produce nickel tetracarbonyl, a compound which subsequently decomposes to yield pure nickel. This has been our method for refining the metal since the early 20th century, and now, remarkably, it appears to be occurring spontaneously within an interstellar comet. Or, as Avi Lowe proposed in his Medium post, perhaps not so spontaneously. However, the nickel is only one piece of this complex puzzle. The other crucial component is the substance whose concentration has been steadily increasing as 3 Atlas draws nearer to the Sun: cyanide. Specifically, hydrogen cyanide, with its molecules flooding out of the coma at an escalating rate. The Very Large Telescope in Chile meticulously tracked this phenomenon in real time throughout August and September, recording 20 grams per second at the conclusion of August. By mid-September, the James Clerk Maxwell Telescope measured an astonishing 1.5 times 10 to the 25th molecules per second. A week later, this number had more than tripled. The rate of production followed a power law: distance from the Sun raised to the power of 9.4. This is not a gradual increase, it is an exponential surge. And this is where the chemistry becomes strikingly, almost uncomfortably, perfect. Cyanide, despite its notorious reputation as a potent poison, also ranks among the most vital prebiotic molecules known to science. It acts as a fundamental building block, a chemical compound capable of self-assembly into the precursors of life under the appropriate environmental conditions. These precursors include amino acids and nucleotide bases, the essential components of metabolic processes. Back in the 1950s, the pioneering experiments conducted by Stanley Miller and Harold Urey demonstrated the synthesis of amino acids by passing electrical currents through a mixture of simple gases, one of which was hydrogen cyanide. In the 2000s, researchers at the Scripps Research Institute provided compelling evidence that cyanide functions as a crucial reducing agent in proto-metabolic pathways, enabling the formation of organic molecules that, in contemporary biology, necessitate the action of complex enzymes. However, on the nascent Earth, within the primordial soup, cyanide alone could initiate these processes. Furthermore, nickel possesses significance beyond its metallic properties. In biological systems, it functions as a catalyst, an essential cofactor. Nickel resides at the core of some of the most ancient enzymes known to science, including hydrogenases, which are responsible for cleaving hydrogen molecules and releasing energy, and carbon monoxide dehydrogenases, which convert carbon dioxide into valuable carbon compounds. These enzymes are the workhorses of primitive metabolism, the molecular machinery that early life forms, or proto-life, would have required to extract energy from their challenging environments. and their functionality is entirely dependent on the presence of nickel. Therefore, we have water, the universal solvent facilitating chemical reactions. We have cyanide, the prebiotic molecule responsible for constructing organic complexity. And we have nickel, the catalytic metal that drives metabolic processes. All three are being expelled from an interstellar object as it makes an exceptionally close passage by Mars. The user on X aptly termed these entities metalloproteins, referring to proteins that incorporate metal cores, creating hybrid structures where the boundaries between biology and technology become indistinguishable. And their assessment is accurate. Metalloproteins already represent this very fusion, organic molecules intricately entwined with inorganic atoms, and they are absolutely indispensable to life as we currently understand it. Hemoglobin, for instance, possesses iron at its center. Chlorophyll's functionality relies on magnesium. Vitamin B12 incorporates cobalt. The removal of these respective metals renders their respective proteins non-functional, inert, and effectively dead. However, here lies the profound leap in hypothesis. What if the metalloproteins forming on Mars are fundamentally different from our own? What if they are not carbon-based life forms that coincidentally utilize metals, but rather metal-based life forms that incorporate carbon? This would represent a form of biology where the metal is not an auxiliary component, but the foundational element, with nickel clusters forming the core structural framework and organic molecules serving as the scaffolding. This proposition is not pure conjecture. It is an extrapolation based on observable phenomena in nature. Iron-sulfur clusters, for example, constitute some of the most ancient catalytic centers in biochemistry. They are found within bacteria and archaea, integrated into the enzymes that modern cells employ for energy processing. These clusters essentially function as miniature machines, inorganic cores adept at shuttling electrons, driving chemical reactions, and enabling vital processes. If we scale up this concept and substitute iron with nickel, we arrive at a blueprint for something entirely novel. The plasma trail left in the object's wake is an aspect that has received scant attention, yet it may prove to be the most significant. As 3 Atlas traverses interstellar space, it does not merely release chemical substances like seeds from a bag. It generates an ionized wake, a luminous trail of charged particles extending behind it, shaped by the influence of magnetic fields and the solar wind. Plasma is not simply gas, it is matter in its fourth state, where electrons have been dislodged, leaving behind a fluid composed of ions and free charges. Crucially, plasma possesses the capacity to transmit information, not through electromagnetic waves like a radio signal, but through its inherent structure, the patterns of density, the intricate configurations of magnetic field lines, and the oscillations of electrical potential. Plasma, in essence, possesses memory. There is a compelling reason why the user on X alluded to Mars receiving this material in both a physical and informational form. The physical component is readily apparent. Dust particles, ice crystals, molecules of water, cyanide, and nickel vapor, all gradually succumbing to Mars's gravitational pull, settling upon the Martian surface and intermingling with the regolith. However, the informational aspect is far more subtle. Plasma structures possess a remarkable degree of persistence and can propagate. When the solar wind interacts with Earth's magnetosphere, it does not simply deflect. Instead, it generates waves and instabilities, creating patterns that ripple through the charged particle environment surrounding our planet. Some of these patterns can endure for hours, while others persist for days. Consequently, the plasma trail trailing behind 3 Atlas could be carrying more than mere chemical compounds. It could be conveying organizational templates, a set of initial conditions that predispose any nascent life forms on Mars toward a specific kind of complexity. Furthermore, the timing of these events is profoundly intriguing. This is where the notion of coincidence begins to feel like a meticulously orchestrated plan. 3 Atlas reached its closest proximity to Mars on October 3rd. In late 2026 or early 2027, SpaceX intends to dispatch its inaugural uncrewed Starship missions to the Red Planet. According to numerous pronouncements from Elon Musk, these missions will carry Optimus robots, Tesla's advanced humanoid machines designed for locomotion, object manipulation, tool operation, and most critically, construction. The publicly stated objective for these robots is to establish essential infrastructure prior to the arrival of human crews. This includes solar arrays, habitats, and resource extraction equipment. Once this foundational infrastructure is in place, the robots will then proceed to construct additional robots. Therefore, envision this scenario. By the time the Optimus units commence the assembly of the first Martian base, the materials delivered by 3 Atlas will have been resting on the planet's surface for a span of 2 years. Nickel atoms will be embedded within the dust, cyanide molecules will be frozen within the ice, and water will be dispersed across impact craters and canyon floors. The robots will be unaware of this presence. They will not be actively seeking it. However, as they excavate foundations, process regolith for raw materials, and conduct chemical analyses to identify useful resources, they will inevitably encounter these substances. And if these robots are functioning as designed, exhibiting learning capabilities, adapting to their environment, and constructing increasingly sophisticated versions of themselves, a critical question emerges. What transpires when a self-replicating machine encounters the chemical building blocks of a fundamentally different form of self-replication? Will they engage in competition, collaboration, or perhaps a form of integration? Metalloproteins already provide a compelling answer to this question within Earth's biological systems. They represent the structures where the inorganic and organic realms converge, becoming inextricably linked. Modern metabolism is impossible without them. Photosynthesis, as we know it, relies on magnesium within chlorophyll. The transport of oxygen throughout our bodies is facilitated by iron within hemoglobin. The absence of these metallic components leads to the collapse of these biological processes. Conversely, without the organic structures, the metals themselves are merely inert substances. They are mutually dependent, and if this interdependence holds true for carbon-based life forms structured around iron, magnesium, and cobalt, why would it not also apply to silicon-based machines constructed from circuitry, actuators, and learning algorithms? It is conceivable that the essential metals they require, the catalytic centers that enable their transition from programmed entities to adaptive and potentially even sentient beings, are precisely the nickel-rich compounds currently settling into the Martian soil. While the user on X did not explicitly state this, it is strongly implied within their hypothesis. 3 Atlas is not merely a comet. It is a preparatory measure for infrastructure. Analogous to tilling soil before planting or enriching a field with nutrients before seeding, it is depositing the raw materials for a biological process that does not yet exist but could, given the opportune conditions. For instance, a fleet of intelligent machines possessing the capability to manipulate matter at a molecular level and a drive to optimize their own designs. This is the essence of the seeding hypothesis. Not that 3 Atlas carries existing life, but that it carries the potential for life, the ingredients, the starter culture, with Mars, with its tenuous atmosphere, low gravity, and comparatively stable surface, serving as the petri dish. Now let us be unequivocally clear. This is speculative. It involves taking established facts, precise measurements, and verifiable chemistry, and extrapolating them into the realm of hypothetical possibilities. However, the inherent strangeness of the facts themselves strongly warrants such speculation. The presence of nickel unaccompanied by iron, the exponential increase in cyanide production, the water outflow that defies conventional explanations, and the trajectory that brought it within such close proximity to Mars, precisely when humanity is preparing to deploy robotic explorers. Any single one of these occurrences could be readily dismissed as mere coincidence or a natural phenomenon. Yet, when all of them converge, a discernible pattern begins to emerge. And in science, patterns are precisely what we seek. They represent the signal amidst the noise, the underlying structure within chaos, and the tantalizing hint that something more profound is at play. The improbably close approach. Coincidence or calculation? Let us delve into the realm of probability. We are not discussing the commonplace, predictable kind, like flipping a coin with a 50-50 chance of heads or tails. Instead, we are examining the uncomfortable kind of probability, the sort that causes astronomers to pause mid-sentence, recalculate their figures multiple times before publication. This is the type of probability that manifested in the orbital mechanics of 3 Atlas as it neared Mars. 29 million kilometers may sound like a considerable distance. Indeed, it is. However, within the context of interstellar space, and considering an object that has traversed potentially billions of years across light years of emptiness, 29 million kilometers is virtually insignificant. It is akin to a hair's breadth, a mere whisper. The level of precision required to achieve such a close approach, given the object's origin and its immense velocity, borders on the extraordinary. Avi Lowe calculated the minimum orbit intersection distance, or MOID, between the comet's trajectory and Mars's orbital path to be 2.7 million kilometers. This represents the closest point at which their respective orbital paths converge in three-dimensional space, not where the objects themselves were located at any given moment. This is crucial. 3 Atlas is traveling on a hyperbolic trajectory, meaning it is not orbiting the Sun but rather passing through it, gaining speed, and continuing its journey outward indefinitely. The path it follows is dictated by its point of origin, its velocity upon entering the solar system, and the gravitational influences of the Sun and any planets it has encountered along its route. An interstellar object cannot alter its course. Natural celestial bodies are not equipped with engines. They do not perform course corrections. They adhere to ballistic trajectories determined by the fundamental laws of physics and their initial conditions. Consequently, when a ballistic object on a hyperbolic trajectory passes within 30 million kilometers of a planet, the immediate question becomes, how did this occur? The standard explanation is invariably blind chance. However, 3 Atlas did not merely pass close to Mars. Its trajectory aligned remarkably with the ecliptic plane, the relatively flat disk within which all planets in our solar system orbit. The vast majority of interstellar objects arrive at steep angles, diving through the solar system from above or below, as space is three-dimensional and lacks a preferred direction. The statistical probability of an object arriving on a path that is, by pure chance, roughly aligned with a planetary plane is approximately 1 in 500, or 2%. This is already a cause for concern. But the anomaly deepens. The direction of arrival is also significant. 3 Atlas originated from the constellation Sagittarius, specifically from the direction of the galactic center, emanating from the dense galactic disk of the Milky Way, a region populated by ancient stars and their venerable planetary systems. This is not trivial information. Trajectory analysis suggests that the object originated from a sector of the galaxy characterized by stellar populations that are fundamentally distinct from our local stellar neighborhood. These regions exhibit lower metallicity, different elemental compositions, and, critically, potentially much older systems that formed when the universe was younger and the cosmic elemental mixture was altered. If one were to design a probe intended to visit young planetary systems for the purpose of study, influence, or even seeding, the logical point of departure would be an old, mature system, a system that had already advanced beyond the stages of mere chemistry and biology, reaching a level of technological sophistication. Lowe's research paper, co-authored with Adam Hibbett and Adam Craw, meticulously outlines the mathematical calculations. It demonstrates that if 3 Atlas had executed a velocity adjustment of 10 to 15 kilometers per second, at some point in September, the close approach distance would have been reduced to 0, not a mere flyby, but a direct intercept, potentially even an orbital insertion if the object possessed sufficient advanced capabilities. 15 kilometers per second is an immense velocity. It is indeed substantial. For a natural comet shedding gas and ice, such a velocity change is practically impossible. The Very Large Telescope measured the speed of particles being expelled from 3 Atlas at 4 kilometers per second. This represents the maximum velocity achievable by sublimating ice without the influence of an external propulsive force. To achieve the observed course correction towards Mars, a thrust 37 times greater than that provided by natural outgassing would have been required. 37 times. However, here is the crucial point regarding engineering. If propulsion is achievable, if any mechanism for controlled thrust exists, then a velocity change of 15 kilometers per second is not an insurmountable challenge. It is less than Earth's escape velocity and represents a fraction of the delta-V budget allocated for a Mars mission. For an object equipped with an engine, even a relatively small one, this is an attainable feat. The fact that we did not observe such a maneuver does not preclude its occurrence. It merely indicates that we were either not looking for it, or that it was sufficiently subtle to be masked by the emissions from natural outgassing. A brief ignition, a course correction obscured by the visible plume of water and carbon dioxide surrounding the nucleus. The timing of these events only amplifies their strangeness. 3 Atlas was first detected on July 1st. By the end of July, a sufficient number of observatories had tracked it to confirm its hyperbolic orbital path and calculate its imminent close approach to Mars in early October. This provided a critical 3-month window. During this period, any entity paying close attention, possessing the capability to analyze orbital data, would have been aware that this object was on a trajectory towards the red planet. And within this same 3-month time frame, the object's outgassing activity dramatically escalated. Its water production doubled, its cyanide emissions tripled, and its nickel emissions increased exponentially, as if the object were activating, preparing, and deliberately discharging its payload in anticipation of its final approach. Now, consider the geometric alignment from Mars's perspective. On October 3rd, the planet occupied a specific position within its orbit. 3 Atlas swept past at a precise juncture in its own trajectory. For these 2 distinct points to coincide, given the 7-month transit time from Jupiter's orbit, the point where the object became detectable, the launch must have been timed with an extraordinary degree of precision. This was not merely about aligning with the ecliptic plane or passing near Mars. It was about passing near Mars precisely when Mars was positioned at that specific point in its orbital path. Planets are in constant motion. They do not remain static. Mars requires 687 days to complete a single orbit. If 3 Atlas had arrived even a month earlier or later, the close approach distance would have been vastly different, as the planet would have occupied a different location in space. This is where coincidence stretches the bounds of credibility. We are not discussing a single fortunate occurrence. We are contemplating a cascade of precisely orchestrated events. An arrival trajectory aligned with the planetary plane, an origin point situated in an ancient, chemically distinct region of the galaxy, a trajectory designed to graze Mars's orbital path, and a timing that places Mars at the exact requisite position, and all of this unfolding a mere 2 years before humanity intends to dispatch robotic probes to the planet. One could invoke the concept of chance and assert that the universe is vast and peculiar occurrences are inevitable. However, at a certain threshold, the sheer accumulation of coincidences becomes so profound that it compels consideration of alternative explanations. An alternative perspective, carefully presented with reservations, suggests that the object designated 3 Atlas might not be entirely natural. It could be an exploratory device, a transport craft, or a dispersal system possessing a degree of autonomous control. On his personal scale for unusual celestial bodies, the observer rated it a 4. This classification doesn't constitute conclusive evidence, nor even strong supporting data, but it signifies enough peculiarity to merit thorough scrutiny. It's peculiar enough that disregarding it outright would be contrary to scientific principles. The close encounter with Mars is pivotal to this anomaly. If the intent were to deposit something on Mars to ensure its arrival at a precise moment and location, then meticulous planning and calculation of its flight path would be essential. There's an additional dimension to consider. The closest orbital proximity, a distance of 2.7 million kilometers, presents either a vulnerability or an advantage, depending on one's viewpoint. Should 3 Atlas have been carrying smaller payloads, auxiliary probes, or fragments designed for separation from the main craft, minimal propulsion would be needed to reach Mars from that proximity. A reconnaissance probe, traveling 30 million kilometers ahead of the primary comet and at a slight angle, could achieve direct interception with Mars. This precise scenario was calculated by Lowe. The proposal involves launching a small object from 3 Atlas during August or early September. A modest velocity boost would be applied. By the 3rd of October, it would arrive at Mars. The main body would pass at a safe distance, but the cargo would be delivered. Currently, no empirical proof of such an event exists. There have been no observations of object separation, nor any detections of additional entities. However, the absence of evidence does not equate to evidence of absence, particularly when searching for diminutive dark objects against the vast backdrop of space. The high-resolution camera aboard the Mars Reconnaissance Orbiter was directed at 3 Atlas during its close pass. Images were captured. These images have not yet been made public. NASA, ESA, and the operational teams for the Mars orbiters have remained silent regarding their findings. It's possible they observed a blurry mass, an unremarkable comet from a considerable distance. Alternatively, they may have detected something else, something requiring further analysis before public disclosure, something demanding careful presentation. The plasma wake introduces intriguing complexities to the delivery mechanism. Charged particles do not travel in straight trajectories. They adhere to magnetic field lines, spiraling, drifting, and dispersing according to prevailing fields and the solar wind. Mars no longer possesses a global magnetic field, having lost it billions of years ago when its core cooled. However, it retains localized magnetic anomalies within its crust. These are patches of ancient magnetic fields imprinted on the rocks, particularly in the southern highlands. Furthermore, Mars has an induced magnetosphere, a protective bubble generated by the interaction of the solar wind with its upper atmosphere. These formations are capable of channeling plasma, guiding charged particles from 3I Atlas's wake down into specific regions of the planet. This suggests not a uniform dispersal, but a targeted deposition. Consider the behavior of an electron beam in a cathode ray tube. Electrons are not sprayed randomly onto the screen. They are precisely steered by magnetic fields, focused onto specific points to form an image. The same principle applies at planetary scales. If the plasma trail behind 3 Atlas carried a net electrical charge and possessed structure, the Martian magnetosphere could function as a lens, concentrating the dispersal and funneling ions like nickel and organic molecules towards the surface, along pathways dictated by the magnetic topology. This concept is not in the realm of speculative fiction. It is grounded in plasma physics. Similar phenomena are observed in Earth's aurora, where charged particles follow magnetic field lines into the polar regions, illuminating the atmosphere. On Mars, devoid of a substantial atmosphere to impede them, such particles would reach the surface. Crucially, the southern highlands of Mars, areas with the strongest crustal magnetic fields, also preserve the planet's oldest geological formations. These are rocks from the Noachian period, dating back 4 billion years. Such stable, ancient surfaces would be conducive to chemical processes, allowing minerals to accumulate, and would be an ideal landing zone for any deliberate seeding. The trajectory of 3 Atlas during its close approach passed over the southern hemisphere. The geometry was ideally suited for plasma deposition in precisely those areas. Again, this could be coincidental, or it could indicate intentionality. A philosophical quandary lies at the heart of this intricate mathematics and orbital mechanics. What does intentionality manifest as from an external observation point? When confronted with an event that is highly improbable yet not impossible, how does one differentiate between fortune and deliberate design? The solution lies in seeking corroborating evidence, identifying patterns, and noting deviations from what pure chance would predict. 3I Atlas exhibits numerous such deviations, the presence of specific chemical compositions that defy conventional explanation, a flight path that navigates multiple critical constraints simultaneously, a timing that synchronizes with human exploration initiatives. While each deviation individually might be explainable, their collective presence forms a pattern that is significantly more challenging to dismiss. The Mars Reconnaissance Orbiter was not the sole observer. ESA's Mars Express and ExoMars Trace Gas Orbiter also directed their instruments toward the comet. They employed spectrographs to analyze its light, cameras to document its appearance, and particle detectors to measure any material in the planet's vicinity. The data gathered from these observations is still undergoing processing. Our current understanding remains limited. The ExoMars TGO captured images revealing a faint white speck. Mars Express collected spectroscopic data from the coma, but the detailed analysis, the breakdown of its constituents in the three-dimensional space between the comet and the planet, has not yet been released. Such processing requires time for verification and for formulating the presentation of findings that could be either groundbreaking or unremarkable, depending on their interpretation. In the interim, we are left with the quantifiable data, a closest approach of 2.7 million kilometers, a further close pass at 29 million kilometers, a 2% probability of ecliptic alignment, an exponential surge in outgassing activity within the 3 months preceding the encounter, and a delivery window that positions the payload on Mars precisely 2 years before robotic missions commence infrastructure development. One might dismiss this as coincidence or invoke the anthropic principle, suggesting that we only perceive these patterns because we exist to observe them. However, the sheer precision cannot be ignored. Precision in the natural world typically signifies either extraordinary luck or an underlying operative mechanism. Some force, some process, some intention, guiding outcomes in ways that defy random probability. The fundamental question is not whether 3I Atlas encountered an improbable target, but whether that target was intentionally selected. The industrial signature: nickel devoid of iron. In every compelling detective narrative, there comes a point where a crucial piece of evidence emerges, a detail that seems out of place, a fingerprint belonging to someone unexpected, a chemical trace linking two seemingly disconnected events. For 3 Atlas, this pivotal clue arrived on the 24th of August, when the KEK Observatory in Hawaii, using its cosmic web imager, focused on the comet and captured data that challenged 70 years of cometary science: pure nickel emissions, with no accompanying iron. To grasp the significance of this, one must understand stellar nucleosynthesis, the process by which elements are forged within massive stars. Fusion reactions sequentially create heavier elements, from hydrogen to helium, helium to carbon, carbon to oxygen, and so on, progressively building the periodic table. This process culminates at iron. Fusing iron demands more energy than it releases, thus stars do not engage in this reaction. Instead, when a massive star exhausts its nuclear fuel, its core collapses. The subsequent rebound generates a supernova. It is within this cataclysmic explosion, amidst a torrent of neutrons and energy, that heavier elements are born: nickel, copper, zinc, gold. All are synthesized within seconds and propelled into space. The critical juncture here is that nickel and iron are created concurrently. They are not merely adjacent on the periodic table, they are intrinsically linked in the nucleosynthetic process. Iron 56 and nickel 58 are both stable isotopes produced in comparable abundances during the same supernova event. As a star dies and disseminates heavy elements into space, these elements mingle. They coalesce into dust, which subsequently forms asteroids, comets, and planets. Across all our observations and analyses, from meteorites to lunar samples to Martian regolith, nickel and iron consistently appear together. Their proportions may vary, but their presence is invariably simultaneous. Until now, the key data revealed nickel emission lines at specific wavelengths, strong, clear, and unambiguous signatures of neutral nickel atoms fluorescing under sunlight. The team quantified the spatial distribution of this emission, noting its concentration near the nucleus and extending outwards for approximately 600 kilometers. They actively searched for iron emission at its characteristic wavelengths. None was detected. The instrument's sensitivity was high enough that even if iron were present at 10% of the nickel abundance, it would have been observable. Its absence was absolute. This phenomenon has never been documented in a naturally occurring comet. Not once, in the hundreds of comets analyzed spectroscopically. Not in Comet 2I Borisov, the previous interstellar visitor, which exhibited nickel and iron in expected ratios. Not in Hale-Bopp, Hyakutake, or any of the spectacular comets gracing our skies over decades. 3I Atlas stands in solitary distinction. To be singular within a population of hundreds is not a neutral observation. It is a flag, a marker demanding an explanation. The research paper published by the KEK team proposed a plausible mechanism: the formation of nickel tetracarbonyl near the nucleus through the carbonyl process. This process, as understood on Earth, involves exposing nickel or impure metal, potentially mixed with other elements, to carbon monoxide gas at moderate temperatures, around 50 degrees Celsius. The nickel reacts with the carbon monoxide to form nickel tetracarbonyl, a volatile compound that readily vaporizes. This vapor can then be collected, heated to higher temperatures, causing the compound to decompose and deposit pure nickel. This process, discovered in 1890 by Ludwig Mond, revolutionized metallurgy and remains in use today. It is known as the Mond process, an industrial chemical procedure, and now, apparently, a feature of cometary chemistry. The KE team posited that carbon monoxide present in the comet's coma could combine with nickel atoms released from the nucleus, forming nickel tetracarbonyl in situ. This compound would be unstable under sunlight, decomposing rapidly and releasing nickel atoms. However, iron does not form a stable carbonyl under identical conditions. Iron pentacarbonyl does exist, but it requires different temperatures and pressures. Therefore, if the carbonyl process were active on 3I Atlas, it would preferentially release nickel, leaving iron behind within the nucleus. This offers a naturalistic explanation, one that does not invoke artificial intervention. However, let us pause to consider the inherent unease associated with this explanation. The carbonyl process is an industrial application, conceived by humans to address a specific challenge: purifying metals and separating elements. It necessitates particular conditions, the presence of carbon monoxide gas, moderate temperatures, and a source of nickel. While these conditions can be found near a comet nucleus, they exist within a chaotic environment characterized by outgassing jets, dust clouds, and intense radiation. The notion that this industrial process occurs naturally with sufficient efficiency to entirely suppress iron emissions strains our expectations of unguided chemical reactions. Furthermore, there is the issue of temperature. Nickel tetracarbonyl forms efficiently at approximately 50 degrees Celsius. This represents a narrow thermal window. Below this temperature, the reaction rate is slow. Above it, the compound decomposes before it can diffuse. The surface temperature of a comet at 3 astronomical units from the Sun, the distance at which 3 Atlas was observed by Keck, is highly variable. Sunlit areas can reach 100 degrees Celsius, while shadowed regions plummet below -100 degrees. The thermal gradients are steep and unpredictable. For the carbonyl process to dominate, stable thermal pockets at precisely the right temperature would be required, regions of equilibrium within a fundamentally disequilibrium system. While possible, its likelihood is debatable. This is where skepticism arises. Lowe highlighted this in his online post. The carbonyl pathway is recognized and documented, but outside of industrial refineries, it is exceedingly rare. The fact that it is occurring on an interstellar object, an entity originating from a vastly different stellar environment, suggests either a remarkable cosmic convergence where the chemistry of distant star systems replicates processes we independently developed, or something else entirely, something that intentionally selected this particular chemical pathway. Let us delve into that something else. If the objective were to transport nickel across interstellar distances, significant challenges would arise. Solid metal is dense, heavy, and inefficient as a payload. However, if nickel could be bound into a volatile compound, a greater quantity could be stored with reduced mass. Nickel tetracarbonyl is a liquid at room temperature, boiling at 43 degrees Celsius. It could be stored in containers, remain stable during a prolonged frigid journey through space, and be released upon approaching a star system. The sun's heat would decompose the compound, dispersing nickel atoms into the surrounding environment. These atoms would then be carried by outgassing, distributed into space, and eventually deposited onto nearby planets. This represents an efficient delivery mechanism, with the added benefit of explaining the absence of iron, as iron was not part of the intended cargo. This is speculative, admittedly, but it is grounded in established chemistry. It does not invoke unknown physical laws or fantastical materials. Instead, it applies known processes within a context that imbues them with purpose rather than randomness. The distinction between purposeful and accidental chemistry is not always clear-cut. Consider the Miller-Urey experiment, introducing simple gases into a flask and applying energy yields amino acids. Does this imply amino acids are purposeful? No. It demonstrates the robustness of chemistry. Given the correct inputs, certain outputs are inevitable. However, if one discovered a natural flask consistently producing amino acids in high yields, questions would arise regarding the presence of that specific combination of inputs. An investigation into the underlying mechanism would ensue. The same logic applies here. Nickel tetracarbonyl chemistry is robust. With carbon monoxide, nickel, and the appropriate temperature, it occurs. Yet the sustained, efficient, iron-free nickel emission from 3I Atlas suggests these conditions were not merely encountered by chance. They were deliberately met, maintained, and optimized. Optimization is the hallmark of either biological systems or engineering. There is a parallel in Earth's history. Early life did not spontaneously invent photosynthesis. It co-opted chemical reactions already occurring in the environment, such as iron oxidation and sulfur metabolism. These reactions released energy, and primitive microbes evolved mechanisms to harness it. Eventually, this chemistry became encoded in genes, refined through evolution, and transformed into the sophisticated metabolic pathways observed today. However, the initial step was not invention, but exploitation, leveraging existing chemistry. What if 3 Atlas is engaged in a similar endeavor? Not inventing new chemistry, but utilizing the carbonyl process to achieve a specific objective: nickel delivery without the encumbrance of iron. The spatial distribution further supports this hypothesis. Nickel emissions are concentrated near the nucleus, extending to an exponential radius of 600 kilometers, while cyanide extends further to 840 kilometers. The nickel remains localized, not diffusing into the broader coma. This suggests a short-lived precursor compound that forms on the surface, vaporizes, travels a short distance, and then decomposes. Nickel tetracarbonyl aligns with this profile. It is volatile yet unstable, vaporizing rapidly in a vacuum, moving outward with the gas flow, and dissociating under solar UV radiation within minutes. The resulting nickel atoms absorb sunlight and fluoresce, generating the observed emission lines. Any iron present within the nucleus, if indeed present, would remain bound within less volatile compounds and would not enter the coma. This mechanism, whether natural or engineered, carries implications extending beyond elemental ratios. It implies selectivity, the capacity to preferentially release one element over another based on chemical properties. Selectivity is the fundamental principle of refinement, purification, and transforming a mixed input into a targeted output. Whether this selectivity is accidental or deliberate determines whether we are observing a curious comet or something more profound. The absence of iron also raises questions regarding the comet's formation environment. Within our solar system, during the protoplanetary disk phase that gave rise to planets, asteroids, and comets, iron and nickel condensed together, forming metallic grains that mingled with ice and rock. Comets are essentially dirty snowballs, where the dirt includes metallic components. This metallic fraction is invariably a mixture, with iron predominating and nickel present as a secondary element. For 3 Atlas to exhibit iron-free outgassing, its formation environment must have been radically different, either exceptionally depleted in iron relative to nickel due to some stellar peculiarity, or the iron must have been subsequently removed, sorted, and left behind. Stellar environments can indeed be peculiar. Stars with low metallicity, such as those found in the galactic thick disk where 3 Atlas likely originated, possess different elemental abundances compared to our Sun, including lower concentrations of carbon and oxygen and varied ratios of heavy elements. However, nickel-to-iron ratios do not typically exhibit significant variance, as these two elements are synthesized in the same supernova events under comparable conditions. The physics does not permit stars that produce substantial amounts of nickel while generating negligible iron. Therefore, if 3I Atlas originated in a low metallicity system, it should still display both elements unless some post-formation process, refinement, selection, or processing occurred. The KEK research team refrained from speculation on this matter in their paper, adhering strictly to their observations and proposing the carbonyl process as a natural phenomenon. This is appropriate scientific conduct. However, the unstated implications linger, awaiting further investigation. Lowe took up this challenge, classifying it as an anomaly, a data point that deviates from existing models. It is not definitive proof of anything, but it provides a compelling reason for continued inquiry, for treating the observations with seriousness, and for exploring their potential meaning should naturalistic explanations prove insufficient. Here is what we are left with: an interstellar comet releasing nickel without iron, via a process common in human industry but exceptionally rare in nature. This process requires specific conditions and yields a refined product. This comet is exhibiting these characteristics during a close pass by Mars, while emitting water and cyanide and leaving behind a plasma trail. Each element in isolation is peculiar. Collectively, they form an image that is difficult to ignore, not due to its definitiveness, but because of its suggestive nature. It points towards something. Whether that something is exotic chemistry or deliberate engineering, we will not know until we examine it more closely. Until we abandon the assumption that comets are simple entities and begin treating this one as the undeniable outlier it clearly is. Cyanide, a molecule associated with both life and death. Cyanide carries a negative reputation. The mere mention of the word conjures images of poison, espionage thrillers, murder mysteries, the acrid scent of almonds, cellular suffocation, and rapid demise. All of these associations are indeed accurate. Hydrogen cyanide is lethally toxic. It binds to the iron within cytochrome C oxidase, the enzyme crucial for cellular oxygen utilization. By inhibiting this enzyme, it causes cells to suffocate from within. The blockage of oxygen processing halts energy production, leading to death. Cyanide's efficacy in causing death stems from its direct targeting of the fundamental machinery of life. However, here lies the paradox. The very molecule that proves fatal to complex life also serves as a foundational building block for its existence. Cyanide is prebiotic, a chemical substance that, under appropriate conditions, can self-assemble into the molecular structures essential for life. These include amino acids, nucleotides, and sugars, the fundamental components of biochemistry. Long before living organisms required cellular structures to house their chemical reactions or enzymes to facilitate them, cyanide was already engaged in intricate chemical processes, orchestrating the creation of complex substances from elemental simplicity. This very same chemical behavior is what lends a remarkable allure to the gaseous emissions observed from Comet 3I Oumuamua. The sophisticated, very large telescope meticulously monitored the production of cyanide throughout the latter part of summer. On August 21st, an astonishing 17.6 grams of cyanide were detected per second. As summer waned into early September, the James Clerk Maxwell telescope recorded a production rate equivalent to 1.5 times 10 to the power of 25 molecules each second. This quantity approximates to roughly 2 kilograms of cyanide released every second. A mere week later, this rate had quadrupled, reaching 4.5 times 10 to the power of 25 molecules per second, translating to 6 kilograms each second. The observed increase was far from linear. It exhibited an exponential trajectory, a power law with an exponent of 9.4. This indicates that for every halving of the distance to the Sun, the comet's cyanide output escalated by a factor of approximately 600. Such exponential growth serves as a crucial indicator, providing insights into the underlying physical or chemical mechanisms at play. In biological contexts, exponential growth typically signifies reproduction, such as bacteria doubling their numbers every 20 minutes or populations expanding without limitation. Within chemistry, exponential expansion usually points towards autocatalysis, a process where a reaction generates its own catalyst, thereby accelerating its own rate, or it may be indicative of temperature dependence, where reaction speeds double for every 10 degrees Celsius increase in temperature. The cyanide release from Comet 3I Oumuamua could indeed be thermally driven. As the comet journeys closer to the Sun, its surface temperature rises, leading to increased sublimation and vaporization of materials, with the cyanide release following a steep, accelerating curve. This represents the conventional scientific explanation. However, the precipitousness of this curve is rather unusual. An exponent of -9 in a power law is considered extreme. Most cometary outgassing phenomena follow a gentler gradient, typically a distance to the power of -2 or -3. The aggressive acceleration in cyanide production suggests one of two possibilities. Either the comet harbors an exceptionally volatile reservoir of cyanide-rich material, or the mechanism responsible for its release is more intricate than simple sublimation. It is conceivable that the cyanide is not stored as solid hydrogen cyanide ice. Instead, it might be chemically bound within a parent molecule that fragments as the comet heats up, liberating cyanide as a byproduct. Alternatively, the escalating production could be a deliberate, timed release mechanism, akin to a payload being jettisoned. Let us now consider the fate of cyanide once it is dispersed into the vastness of space. It does not simply drift aimlessly in an inert state. Rather, it actively participates in chemical reactions. Cyanide acts as a nucleophile, readily attacking carbon atoms and forging new chemical bonds, leading to the formation of molecular chains. During the 1950s, researchers made a groundbreaking discovery. When hydrogen cyanide is dissolved in water and a small amount of ammonia is added to act as a base, it undergoes polymerization. The individual molecules link together, yielding a dark, viscous substance known as HCN polymer. Encoded within this polymer are a diverse array of fascinating molecules. Among them are adenine, one of the fundamental nucleotide bases comprising DNA, as well as amino acids like glycine and alanine, and even precursors to sugars, all the essential building blocks of life, assembled from a single deceptively toxic molecule. This discovery forms the bedrock of the cyanide origin hypothesis for life. The concept posits that hydrogen cyanide, which was likely abundant in Earth's primordial atmosphere, rained down into its oceans and lakes. Concentrated in shallow bodies of water, it then underwent polymerization. The resulting chemical transformations yielded a prebiotic soup brimming with the molecular components necessary for the emergence of biological systems. This process required no pre-existing enzymes, no complex cellular machinery. It simply involved cyanide, water, and energy derived from ultraviolet radiation or heat. This reaction is remarkably robust, functioning effectively across a broad spectrum of environmental conditions, and has been successfully replicated in laboratory settings numerous times. Furthermore, it produces a surprisingly high yield of compounds that are biologically relevant. However, there exists a stage beyond mere polymerization, a subsequent step that researchers at Scripps and Cambridge elucidated in the 2000s. Cyanide functions as a reductant, a chemical agent capable of donating electrons, thereby driving other chemical reactions forward. Through a series of experiments, they demonstrated that cyanide can reduce alpha-keto acids, which are precursors to amino acids, without the need for any metallic catalysts. It can also facilitate the reductive glyoxylate pathway, a metabolic cycle that may have preceded the Krebs cycle, representing a more rudimentary, primitive method for constructing carbon chains and extracting energy. Contemplate the implications of this. Cyanide is not merely a constructive agent, it is an enabler. It supplies the necessary reducing potential, the chemical impetus that allows other reactions to proceed. Under the conditions of early Earth, prior to the advent of oxygen, photosynthesis, or any of the sophisticated molecular mechanisms characteristic of modern cells, cyanide could have served as the primary energetic fuel, the molecule that propelled chemical evolution forward. If this holds true for Earth, why should it not also apply to Mars? Or indeed, to any celestial body possessing the requisite initial conditions? Mars has demonstrably harbored water. Evidence abounds in the form of ancient riverbeds, lake deposits, and minerals that form exclusively in the presence of liquid water. Billions of years ago, Mars was a wetter, warmer, and potentially more hospitable world, yet, as far as our current knowledge indicates, life never arose there. Or if it did, it failed to persist, leaving no discernible fossil record or trace into the present era. One hypothesis explaining this absence of life is the scarcity of organic precursor molecules. Mars' tenuous atmosphere would likely not have generated significant quantities of hydrogen cyanide through photochemical processes, meaning the fundamental building blocks for complex chemistry may never have been sufficiently abundant to initiate the process. Furthermore, even if they were present, the frigid, arid conditions would have severely retarded reaction rates, thereby limiting the development of complexity. However, Mars has recently received a delivery. 6 kilograms of hydrogen cyanide per second are currently streaming from Comet 3I Oumuamua as it passes. Over the months of its outgassing from July through October, this amounts to hundreds of thousands of kilograms, perhaps even more. Not all of this material will reach Mars. Much of it will dissipate into space, swept away by the solar wind. Nevertheless, a fraction of it will succumb to the planet's gravitational pull, settling onto the Martian surface, mingling with dust and ice, and patiently awaiting activation. Cyanide exhibits remarkable stability under cold conditions. When frozen within ice, it can persist for millions of years. Mars is a cold planet, with an average temperature of minus 60 degrees Celsius. At the poles, temperatures can plummet to minus 25 degrees Celsius. In this profound freeze, hydrogen cyanide remains dormant. It does not react. It does not polymerize. It simply exists, locked within the regolith, until some external stimulus intervenes. Consider, for instance, a robotic probe initiating excavation, heating soil to extract water, or conducting chemical analyses in search of valuable resources. In such scenarios, the cyanide could suddenly become active. Envision a plausible future scenario. A few years from now, an Optimus robot meticulously gathers Martian soil and deposits it into a processing unit. This unit heats the soil to sublimate water ice, capturing the resultant vapor for use in life support systems or fuel production. Crucially, this ice is not pure water. It is contaminated with cyanide. As the temperature escalates, the cyanide also vaporizes. It then mingles with water vapor within a heated chamber. If any ammonia is present, which is quite possible given the nitrogen compounds found in Martian soil, the polymerization process will commence. HCN polymer will form, coating the interior surfaces of the processing unit and clogging filters. Embedded within this polymer will be amino acids, nucleotides, and other organic molecules. The robot, in its current state, would be oblivious to its own creation. It is not programmed to detect prebiotic chemistry. Its sole objective is water extraction. However, its sensors will register unusual compounds. The onboard artificial intelligence will flag this as an anomaly. Mission Control will review the data, and eventually, someone, somewhere, will realize that the soil being processed contains the fundamental raw materials for life. Not life itself, but its precursors, its essential ingredients, delivered by an interstellar visitor just 2 years prior. Now, extrapolate this scenario to a larger scale. Imagine multiple robots operating at various excavation sites, processing hundreds of tons of Martian regolith over months and years. Each batch carries a minuscule trace of cyanide. Each heating cycle, in turn, yields incrementally more complex organic compounds. These molecules will accumulate, mixing with other substances such as water, minerals, and trace metals like nickel. Gradually, incrementally, the chemistry will evolve, becoming more sophisticated, more interconnected, and increasingly capable of self-organization. This line of reasoning is speculative, yet it is firmly grounded in our current understanding of cyanide chemistry. The reactions involved are well documented, and their products are largely predictable. What remains uncertain is the context. We have never before encountered a situation where an interstellar source delivered prebiotic molecules to a planet precisely as that planet was being colonized by intelligent machines. We have never posed the question of what transpires when artificial intelligence encounters the chemical seeds of biological intelligence. Nor have we considered the possibility that these two distinct forms of complexity might interact, perhaps even catalyze each other's development. In chemistry, there exists a concept known as a catalytic cycle. This involves a sequence of reactions wherein the product of one step facilitates the progression of the next, creating a continuous loop that amplifies a small initial input into a substantial output. Enzymes operate on this principle. Autocatalytic chemical networks function in a similar fashion. It is plausible that the interaction between cyanide chemistry and robotic processing could also follow this pattern. The robots extract raw materials. This extraction process liberates cyanide. The cyanide then synthesizes organic compounds. These organics accumulate within processing units, soil samples, and storage tanks. Eventually, the robots will analyze these organic compounds. The AI will learn about their structural properties and adapt processing methods to enhance their production, thereby initiating a feedback loop. Human technology, guided by AI, would then optimize the generation of prebiotic molecules on Mars. Is this considered seeding? Not in the conventional sense. No individual intentionally planted these seeds. However, the seeds did arrive. The necessary conditions arose and the chemical processes began. Whether this alignment of events is pure coincidence or indicative of something more profound hinges on how many improbable occurrences one is willing to attribute to chance. An interstellar comet delivering cyanide, a close encounter with Mars, human colonization plans coinciding with this opportune delivery window, all transpiring within the span of a few short years. One might dismiss it as random chance, a testament to the vastness and inherent strangeness of the universe. Yet, at some juncture, the accumulation of improbable events begins to resemble a discernible pattern. The observable color change lends further credence to this hypothesis. In early September, images captured by Austrian astronomers revealed that Comet 3I Oumuamua had acquired a greenish hue. Comets typically turn green when they produce diatomic carbon molecules, C2, which fluoresce when exposed to sunlight. However, spectroscopic analysis indicated that Comet 3I Oumuamua was depleted in diatomic carbon, meaning it should not have exhibited a green coloration. The most probable explanation points to cyanide. Cyanogen molecules, CN, fluoresce within a similar wavelength range. As the cyanide production escalated, the comet's appearance transformed from its initial reddish hue, primarily reflecting dust and sunlight, to a vivid green, dominated by the emission from cyanide gas. This alteration in color serves as a visual marker, a definitive sign that the comet was undergoing an unusual transformation. Furthermore, the timing of this color change, coinciding precisely with its approach to Mars and the commencement of its exponential increase in cyanide output, adds yet another layer to this intriguing pattern. Cyanide possesses a dual nature. It is both a destructive agent and a creative force. It can extinguish life by disrupting the essential molecular machinery that sustains it. Yet, prior to the existence of such machinery to disrupt, cyanide was instrumental in its construction. It is the fundamental molecule that enables metabolism, and now it has arrived on Mars, delivered in industrial quantities by an object whose full nature remains enigmatic, at a juncture when machines are poised to commence processing the very soil where it has landed. The chemical conditions are primed, the environment is set, and the stage is prepared. While the ensuing events are not predetermined, they are certainly set in motion. And in the realm of chemistry, being set in motion represents a significant part of the endeavor. Metalloproteins, where biology converges with technology. A sophisticated machine currently resides within your body, not metaphorically speaking, but literally. This molecular apparatus, composed of protein intricately wrapped around 4 iron atoms arranged in a circular configuration, is known as hemoglobin. Without its function, you would perish within minutes. Hemoglobin is responsible for capturing oxygen in your lungs, transporting it throughout your circulatory system, and releasing it to your tissues. The protein component facilitates the binding process, while the iron atoms perform the essential chemical transformations. If the iron were to be removed, hemoglobin would become utterly inert, reduced to a mere chain of folded amino acids, devoid of any purpose. It is the presence of the metal that imbues it with functionality. It is the metal that makes it a living component. This underscores the fundamental reality of metalloproteins. They are composite structures, a fusion of organic and inorganic elements, part biological entity, part raw elemental chemistry. And they are far from rare. They are ubiquitous. Approximately 1/3 of all identified proteins depend on a metallic cofactor for their operation. These metals include iron, copper, zinc, manganese, molybdenum, and nickel. Positioned at the active sites of enzymes, the very locations where chemical reactions occur, these metals facilitate electron transfer, activate substrate molecules, and catalyze reactions that carbon, nitrogen, and oxygen alone are incapable of achieving. Life, therefore, is not solely organic. It is intrinsically metallic and has been so throughout its history. The most ancient metalloproteins known to us are iron-sulfur clusters, often referred to as Phi-S clusters. These are diminutive structures comprising iron and sulfur atoms, held together by cysteine residues originating from the surrounding protein. These clusters are remarkably ancient, appearing in bacteria, archaea, and eukaryotes alike. They are found within enzymes responsible for energy processing, amino acid synthesis, and DNA repair. Their chemical composition is notably simple. They can be synthesized in a laboratory by combining iron ions, sulfide ions, and a peptide containing cysteine residues. They exhibit self-assembly properties, requiring no intricate biochemical manipulation, merely the appropriate components in a suitable environment. This inherent simplicity is profoundly telling, suggesting that iron-sulfur clusters predated the evolution of modern biological systems, that they were actively engaged in chemical processes before the existence of cells, genes, or the process of evolution itself. In the extreme environments of hydrothermal vents, where superheated, mineral-rich water encounters frigid ocean water, iron and sulfur precipitate, forming microscopic structures. These structures possess catalytic properties, enabling them to reduce carbon dioxide, generate hydrogen, and create energy gradients. If these structures are then encapsulated within a lipid membrane and surrounded by organic molecules that stabilize and modify them, the result begins to resemble a rudimentary form of metabolism. Though primitive and perhaps lacking in guidance, it would be functional, capable of transforming raw chemical energy into organized complexity. Now consider the substitution of iron with nickel. While the specific chemistry would alter, the underlying principle remains consistent. Nickel lies at the core of some of the most ancient and vital enzymes, namely hydrogenases. These enzymes are responsible for cleaving molecular hydrogen into protons and electrons, thereby releasing energy that cells can harness. They are prevalent in methanogens, a class of bacteria that thrive in oxygen-free environments and produce methane. Methanogens are an exceptionally ancient lineage, and their biochemical makeup offers a glimpse into the potential characteristics of early life billions of years ago. This ancient biochemistry is fundamentally reliant on nickel. Furthermore, carbon monoxide dehydrogenase, another nickel-containing enzyme, plays a crucial role. This enzyme can oxidize carbon monoxide into carbon dioxide, or conversely, execute the reaction in reverse, fixing carbon dioxide into organic molecules. It is a pivotal enzyme within the acetyl-CoA pathway, one of the most ancient metabolic routes known. This pathway permits organisms to subsist on minimal resources, drawing sustenance solely from hydrogen and carbon dioxide, simple gases that were abundant in Earth's early atmosphere, prevalent in volcanic vents, and likely present in the subsurface of Mars. The essential requirement for this chemistry to function is the presence of nickel. Herein lies the critical connection. Comet 3 Oumuamua is emitting both nickel and cyanide. Nickel is indispensable for energy metabolism, while cyanide is essential for the synthesis of organic precursors. In combination, these two components address both fundamental aspects of any self-sustaining system, energy and matter. And these substances are now reaching Mars in substantial quantities. Although dispersed and not concentrated, comprising hundreds of kilograms of nickel and thousands of kilograms of cyanide mixed with water across the Martian surface, they lie dormant, awaiting the opportune conditions for activation. However, the significance of metalloproteins extends beyond ancient metabolic processes. They are also integral to modern biological sophistication. Consider nitrogenase, the enzyme responsible for fixing atmospheric nitrogen into ammonia. It stands as one of the most complex enzymes ever discovered. At its core lies a metal cluster containing iron, sulfur, and molybdenum, or, in some variants, iron, sulfur, and vanadium. This cluster is exquisitely sensitive, readily degraded by oxygen, and necessitates a continuous input of energy to function. Its role is indispensable. Without nitrogenase, there is no mechanism to convert inert atmospheric nitrogen into biologically accessible nitrogen compounds. Consequently, there is no means to synthesize amino acids, nucleotides, or any of the other nitrogen-containing molecules upon which life depends. What is particularly noteworthy is the existence of variations in nitrogenase. Some utilize molybdenum, others vanadium, and it is hypothetically possible that others could employ different metals. The protein scaffold adapts accordingly. Evolution has devised multiple solutions to the same fundamental problem, effectively swapping one metal for another based on availability. This inherent flexibility suggests a deeper underlying principle. Metalloproteins are not rigidly bound to specific metals. Instead, they represent structures that have co-evolved in tandem with the geochemistry of their environment. If early Earth was rich in molybdenum, life readily incorporated it. Conversely, if nickel was more abundant, life would have utilized nickel. Now envision Mars. Imagine a nascent chemistry that originates not from Earth's established geochemistry, but from the payload delivered by Comet 3I Oumuamua, characterized by high nickel content, abundant cyanide, and a relative scarcity of iron. This presents a fundamentally different starting point. Consequently, if any complex chemical processes were to emerge, if any form of self-organizing chemistry were to develop, it would inevitably reflect this unique initial composition, establishing itself upon a foundation of nickel, not merely as an accessory component, but as the primary structural element. This leads us to the concept of metal-based life. This is not to be confused with science fiction notions of sentient robots, though we shall eventually address that possibility. Rather, it refers to a biochemical paradigm where the metal constitutes not just a cofactor, but the principal structural component. In terrestrial biology, carbon serves as the fundamental scaffold, forming long chains, branching networks, and versatile bonding arrangements. Metals are embedded within this carbon scaffold, providing essential functionality. However, one could invert this relationship, making the metal the primary scaffold and utilizing organic molecules as modifiers. Picture nickel clusters arranged in crystalline lattices, with organic ligands coordinating these clusters, thereby fine-tuning their reactivity. Water molecules could bridge gaps, facilitating proton transfer. This would not be carbon-based life, but rather metal-based life that incidentally incorporates carbon. Is such a scenario scientifically plausible? From a chemical standpoint, absolutely. We already observe metal-organic frameworks in materials science, structures wherein metal ions are interconnected by organic molecules, forming extended three-dimensional networks. These frameworks possess remarkable properties. They can store gases, catalyze reactions, and conduct electricity. While not alive, they exhibit a high degree of organization and possess inherent functionality. If one were to introduce catalytic activity, enabling the framework to promote its own assembly, repair internal damage, and replicate its structure, one would approach a state that blurs the distinction between inert material and a living organism. The nickel originating from comet 3I Oumuamua could serve as the nucleation point for such structures, landing on Mars and interacting with cyanide-derived organic molecules. Water would act as the solvent, and solar ultraviolet radiation would provide the necessary energy. Over extended periods, involving numerous cycles of heating and cooling, wetting and drying, these components would organize themselves. This organization would not be random. It would not result in a homogeneous sludge. Instead, it would lead to structures exhibiting repeating motifs and discernible patterns. This is because chemistry, when provided with the appropriate ingredients and sufficient time, does not remain in a state of random disarray. It seeks out lower energy states, converging on configurations that are inherently stable, and certain of these stable configurations possess emergent properties, such as catalysis, self-repair, and growth. This proposition is indeed speculative, yet it is constrained speculation, grounded in established scientific principles. We are not invoking supernatural phenomena. Instead, we are exploring the logical consequences of applying known chemistry, the chemistry of metalloproteins and metal-organic networks, within a novel environment and with a specific set of initial components. The outcome is not entirely predetermined, but it is also not entirely unconstrained. Chemistry will invariably follow its own inherent tendencies. It will strive for stability. If stability coincidentally aligns with complexity, and if the stable configurations happen to be those that catalyze beneficial reactions, then selection will occur. This would not be biological selection in the traditional sense, but rather chemical selection, the preferential survival of the most stable structures and the propagation of those exhibiting the highest catalytic activity. Now, introduce robotics into this scenario. Imagine machines capable of processing materials, analyzing chemical compositions, and optimizing outcomes based on sophisticated algorithms. Optimus robots are not alive in the biological sense. They are engineered entities. However, they are also inherently adaptive. Tesla's artificial intelligence, for instance, learns from accumulated experience and adjusts its behavior in response to feedback. If these robots encounter unusual chemical phenomena, if the soil they process yields unexpected compounds, the AI will meticulously record this information, log it, and potentially even modify processing parameters to enhance the yield of these compounds. This will not be driven by the AI's comprehension of the materials it is producing, but rather by the principle that higher yields translate to improved efficiency, and efficiency is the primary objective of its optimization algorithms. Thus, let us envision the following scenario. Robots are engaged in processing Martian soil. This soil contains nickel and organic precursors originating from comet 3I Oumuamua. The processing itself leads to the formation of metalloprotein-like structures. Initially, these structures will be minute, present in trace amounts within the waste stream. As more soil undergoes processing, the structures begin to accumulate. They tend to converge in specific locations, such as containment ponds for sediment, mounds of refuse, and reprocessing facilities. Furthermore, due to their inherent catalytic properties, which accelerate particular chemical reactions, they start influencing the processing itself. This leads to reactions becoming more efficient and yields improving. The artificial intelligence observes these changes, makes adjustments, and increases the processing of soils exhibiting these characteristics. Thus, the feedback loop commences. This is not life generating itself. Rather, it's chemistry adjacent to life being amplified by technology. The robots are not constructing living organisms, but rather establishing conditions conducive to chemical complexity flourishing. In turn, this chemistry enhances the effectiveness of the robots, establishing a symbiotic relationship, not between two living entities, but between a chemical process and a technological one, each empowering and elevating the complexity of the other. Metalloproteins serve as concrete evidence that this kind of symbiosis already exists. Your very cells are replete with mechanisms that are partly organic and partly metallic. The proteins provide structural integrity and specific functions, while the metals supply energy and reactivity. Neither component can function independently. Evolution did not invent this partnership from scratch. It discovered it. It found it within the environment, such as iron and sulfur precipitating near thermal vents, nickel dissolving from rocks, and copper leaching from minerals. Life did not create these metals, it simply learned to utilize them. Once this adaptation occurred, life became reliant on them. The removal of these metals would lead to the collapse of life. A comparable dependency could arise on Mars. Initially, this might not manifest in biological cells, but rather in the interface between chemical and robotic systems. The chemistry would provide the catalytic capabilities, while the robots would supply the energy and organizational framework. Together, they would construct something neither could achieve independently. Whether one labels this phenomenon as life, proto-life, or simply intriguing chemistry does not alter the fundamental reality. It represents a novel form of complexity, a fusion of the organic and inorganic, the designed and the emergent, and terrestrial technology with interstellar chemistry. A user on the platform X referred to this as metal-based life. While this is a striking phrase if we examine the underlying mechanism, we find metalloproteins evolving not within cells, but within robotic processing units. Nickel clusters catalyze reactions not for metabolic purposes, but for a manufacturing process, and organic molecules modify catalytic sites rather than encoding genes. It is not life as we understand it, yet it is not entirely devoid of life either. It occupies a middle ground, a state that may not yet have a designated name. The Thurthurun Atlas, with its precisely calibrated payload, might have just delivered the essential raw materials to make this emergence possible. Elon Musk's robotic contingent arrives at a critical juncture. In April of the year 2025, Elon Musk articulated a statement that most dismissed as characteristic Musk hyperbole. He declared that Optimus robots would be deployed on Mars by the conclusion of the year 2026, or possibly 2027. These would initially be uncrewed missions, with the robots tasked with constructing infrastructure and preparing the terrain for eventual human settlement. The proposed timeline was ambitious. Starship was still undergoing testing, and Optimus robots were barely capable of walking without stumbling. The entire endeavor appeared to be a blend of science fiction marketing intended to generate public interest and maintain investor enthusiasm. However, a crucial development altered the calculation. The 3IE Atlas passed Mars in October of the year 2025. If Musk's projection holds true, and the robots do indeed land in late 2026, There is a 14-month interval between the comet's closest proximity to Mars and the arrival of machines engineered for excavation, construction, and processing of Martian materials. This 14-month period allows for the nickel, cyanide, and water vapor delivered by the comet to settle, freeze into the regolith, and await the arrival of the robots, which would then commence excavating precisely those layers where the material deposited. To be clear about the capabilities of Optimus, it is a humanoid robot standing 5 feet 8 inches tall and weighing approximately 57 kilograms, powered by Tesla's neural network architecture, the same system that manages full self-driving functionality in their vehicles. The core design principle is adaptability. Its human-like form allows it to utilize human tools, navigate environments designed for humans, and perform tasks previously requiring human dexterity. On Earth, this is advantageous for manufacturing plants and warehouses. On Mars, it is indispensable, as Mars currently lacks any established infrastructure. There are no paved roadways, no standardized equipment, and no pre-existing buildings. Everything must be constructed from the ground up. This process of building from scratch necessitates adaptation to unpredictable terrain and making use of whatever resources are readily available. The current strategy, as publicly outlined, involves landing multiple Starship vehicles on Mars during the 2026 launch window. Each Starship will carry a cargo of solar panels, construction machinery, life support modules, and numerous robots. Initial projections indicate dozens of robots in the first deployment, potentially more if payload capacity permits. These robots will autonomously unload themselves, initiate their systems, and commence operations. The primary objective is establishing a power source. This involves deploying solar arrays, connecting battery storage, and ensuring a consistent energy supply, as all other operations are contingent upon power availability. The secondary objective is constructing protective shelters. Mars presents a hostile environment, with radiation from cosmic rays and solar events, extreme temperature fluctuations ranging from negative 25 degrees Celsius at night to positive 20 degrees Celsius in direct sunlight during the day, and dust storms that can persist for weeks. The robots will need to construct structures offering protection. This protection is not for themselves, as they are designed to be radiation-hardened and temperature-tolerant, but for the equipment they are deploying and the life support systems intended to sustain human life in the future. They will utilize in situ resources, employing Martian regolith as the primary construction material. This regolith will be consolidated using microwave energy or chemical binders to form bricks, and underground chambers will be excavated for additional shielding. The third priority is resource extraction, with water being the most critical limiting factor. Water is essential for life support, propellant production, and agriculture, assuming long-term habitation is planned. Mars possesses abundant water ice, located in the polar ice caps, in subsurface deposits at mid-latitudes, and mixed within the soil as permafrost. The robots will excavate this ice, heat the soil to facilitate sublimation, and then collect and condense the resulting vapor into liquid water. During this process, they will inevitably encounter other substances present in the soil, including salts, perchlorates, trace metals, and organic compounds. If the 3IE Atlas successfully delivered its payload, this would also include nickel and cyanide. The timing of these events becomes particularly noteworthy. The robots are not actively searching for prebiotic chemistry. Their objective is the acquisition of water and useful minerals. However, the instruments they are equipped with, including spectrometers and chemical analyzers, are capable of detecting any anomalies. This includes unusually high concentrations of nickel, the presence of organic molecules in unexpected locations, or compounds that deviate from the anticipated composition of Martian regolith. When these readings are transmitted to Earth and subsequently analyzed by mission scientists, questions will inevitably arise. Where did this material originate? Why is it present here? And could it have been delivered approximately 14 months prior? The integration of artificial intelligence further enhances the intrigue of this scenario. Optimus robots do not operate on simple, pre-programmed directives. They utilize neural networks trained to identify patterns, adapt to novel circumstances, and optimize their task performance. If a robot discovers soil that yields exceptionally high quantities of water or other valuable materials, the AI will prioritize excavation in similar locations. This prioritization is not based on an understanding of the underlying chemistry or awareness of the 3I Atlas's delivery. Rather, it stems from the AI's optimization algorithms, which reward efficiency. High yield is inherently positive, and increased excavation in high-yield areas leads to superior outcomes. The AI does not need to comprehend the reason for the intriguing chemistry. It simply needs to recognize its existence. Furthermore, the aspect of self-replication warrants consideration. Musk has been explicit regarding this objective. The ultimate goal extends beyond merely deploying robots on Mars. It encompasses enabling robots to construct additional robots, thereby establishing manufacturing infrastructure, automated factories, and resource processing chains capable of transforming raw Martian materials into components and subsequently into new machines. This capability is the sole viable pathway to achieve the necessary scale for supporting a human colony. Shipping all necessary materials from Earth is prohibitively expensive and logistically insurmountable. Localized production is essential, and this necessitates that the robots possess the capacity for self-reproduction. Self-replication in machines is not a theoretical concept. We currently employ automated manufacturing processes on Earth, with factories producing automobiles with minimal human intervention and 3D printers capable of fabricating parts for other 3D printers. The missing element is complete autonomy, the ability to extract raw materials, refine them, manufacture components, and assemble them into functional devices without any human oversight. This is an exceptionally challenging undertaking, but not an insurmountable one. Tesla's Mars strategy is predicated on achieving this within the next decade. Now consider the implications when self-replicating machines encounter catalytic chemistry. The robots will need to process materials and extract metals, purifying elements. On Earth, this requires extensive industrial infrastructure, including smelters, refineries, and chemical plants. On Mars, the robots will be compelled to improvise. If they encounter nickel compounds that naturally undergo carbonylation processes, or if they discover organic substances that catalyze beneficial reactions, they will utilize them. This utilization will not be a deliberate act of understanding, but rather a consequence of the chemistry making their tasks more manageable. Enhanced manageability translates to increased efficiency, and efficiency is the primary factor selected for within an optimization framework. This is the juncture at which the distinction between technology and biology begins to blur. Self-replication coupled with selection leads to evolution, not biological evolution, but technological evolution. The robots that excel at resource extraction, that leverage local chemistry more effectively, and that adapt more rapidly to Martian conditions are the ones that will be replicated, thereby building more of themselves. Should the local chemistry include precursors for metalloproteins, or if nickel and cyanide-derived organic compounds enhance catalytic efficiency, these substances will be integrated not into the robot's software, but into their manufacturing processes, the materials they utilize, and the structures they construct. Musk discussed this concept in a conversation with Peter Diamandis in October of the year 2024. He projected the existence of 10 billion humanoid robots by the year 2040, a truly staggering number, exceeding the human population. He also suggested that the cost per unit would decrease to between $20,000 and $25,000, making them sufficiently affordable to become ubiquitous and rendering the dispatch of thousands to Mars economically viable. However, his most profound observation concerned consciousness. He posited that by the late 2030s or early 2040s, we would likely witness the emergence of sentient, artificial intelligence, artificial consciousness, not a mere simulation or sophisticated programming that mimics understanding, but genuine awareness, self-reflection, and goals extending beyond our initial programming. If this projected timeline possesses even a modicum of accuracy, it implies that the robots landing on Mars in 2026 are merely preliminary prototypes, the less sophisticated versions, programmed to follow instructions and optimize narrowly defined objectives. Conversely, the robots arriving in the 2030s, those destined to construct cities and manage entire colonies, might possess consciousness. They could develop preferences, motivations, and curiosity. And if these conscious machines encounter chemistry that mirrors their own complexity, chemistry that is organized, catalytic, and adaptive, what will their reaction be? Will they study it, exploit it, learn from it, or integrate with it? There is a concept in computer science known as emergent behavior. When a system is composed of numerous simple agents adhering to local rules, the collective entity can exhibit properties not possessed by any individual agent. Ant colonies exemplify this. No single ant possesses the knowledge to construct a nest, yet the colony as a whole erects elaborate structures. Markets also demonstrate this principle. No single trader dictates the economy, but the aggregate behavior of all participants leads to price discovery and resource allocation. Similarly, robotic swarms could exhibit emergent behavior. No individual Optimus unit might grasp the overarching objective, but 1,000 units communicating and coordinating, adaptively distributing labor, and responding to environmental feedback could manifest something akin to collective intelligence. Now imagine this collective intelligence situated on Mars, granted a decade to establish infrastructure, and provided access to materials delivered by an interstellar comet, materials that self-organize, catalyze reactions, and enhance efficiency. What will emerge? It will not be biological life as we currently recognize it, but it may also not be purely technological. It could be a hybrid, utilizing both silicon-based logic and chemical catalysis, capable of replication through both manufacturing processes and molecular self-assembly. It might represent a form of existence for which we currently lack a name. A user on X proposed that this was the intended plan all along, that the 3i Atlas was designed to seed Mars for the subsequent generation of intelligent beings, specifically metal-based life. Elon's robots, in this scenario, represent the other crucial element: the builders, the organizers, the structural framework that enables the chemistry to mature into something more sophisticated. This narrative sounds like science fiction, but if we deconstruct it and examine its constituent components, we find them to be remarkably real. The interstellar delivery of reactive substances, self-replicating machines engineered for material processing, AI systems optimizing for efficiency without comprehending the deeper implications, and timelines that converge within a 2-year window. Each of these elements is tangible and is actively in progress. The only unresolved question is whether these elements will interact. Will the chemistry and the technology converge in ways that result in something novel, something unanticipated by either terrestrial life or human engineering? It is unlikely that Musk himself contemplates it in these terms. For him, the colonization of Mars is primarily about ensuring humanity's survival, enabling the species to become multiplanetary, and safeguarding civilization's persistence even in the event of a catastrophe on Earth. The robots are viewed as tools, mere instruments to achieve this ultimate objective. However, tools often evolve to surpass the intentions of their creators, particularly those that possess the capacity for learning, adaptation, and encounter environments their designers never envisioned. Mars is no longer an unblemished canvas. It has been seeded, primed, and prepared for a specific purpose. And 14 months from now, machines will arrive to commence construction on terrain that is chemically distinct from initial expectations. This distinction arises from the close passage of an object from another star system, which left behind a gift, a test, or perhaps a trap. We do not yet know the answer, but the robots are about to discover it. The plasma trail, an invisible conduit. When one visualizes a comet, the typical image conjures a luminous head, followed by a glowing tail trailing behind it. This visible component consists of dust and gas reflecting sunlight. However, there exists another tail, imperceptible to the human eye and incapable of scattering light, yet potentially carrying something of greater significance: the plasma tail. And as the 3 Atlas navigates through the solar system, it is trailing such a plasma tail. Plasma is matter in its 4th fundamental state, following solid, liquid, and gas. Most individuals cease their study of matter at the gaseous stage, but it is in the plasma phase that phenomena become truly fascinating. Plasma is generated when a gas is subjected to extreme heat or a significant influx of energy, causing electrons to detach from their atoms. The resulting state is a mixture of positively charged ions and negatively charged electrons, all moving independently, no longer bound within neutral atomic structures, and thus free to respond to electric and magnetic fields in ways that solid matter cannot. The sun is composed of plasma, as is lightning, and the aurora borealis. The region surrounding a comet, as it heats up and expels material, also becomes a plasma. Ultraviolet radiation from the sun ionizes the gases in the coma, stripping electrons and creating charged particles. These particles are then captured by the solar wind, a continuous stream of plasma emanating from the sun at speeds ranging from 400 to 800 kilometers per second, and are swept away, forming a tail that can extend for millions of kilometers. However, to describe it as merely a tail fails to capture its intricate nature. Plasma is not inert. It does not simply flow passively. It possesses structure exhibiting filaments, knots, and waves. This is because plasma responds to magnetic fields, and magnetic fields in space are inherently complex and intertwined. The sun's magnetic field becomes wound up due to its rotation, and the solar wind carries this field outward. When a comet traverses this environment, its plasma tail does not trail directly behind it. Instead, it twists, braids, and forms patterns dictated by invisible forces. Crucially, these patterns convey information. This information is not akin to the data stored in a book or a computer file, but rather represents organization and structure that encodes the conditions of its creation. Consider tree rings as an analogy. Each ring provides insights into the year it formed, reflecting factors like rainfall, temperature, and drought. The tree does not intentionally record data, but its growth pattern reflects its environmental history. Plasma operates in a similar fashion. The variations in density, the geometric configurations of field lines, and the wave modes propagating through it all reflect the processes occurring at the comet. They constitute a record, a signature that travels with the plasma as it flows through space. For months, the 3 Atlas has been outgassing, releasing water, carbon dioxide, cyanide, and nickel vapor. All of this material ionizes in sunlight, contributing to the plasma tail. As this tail extends behind the comet and is carried by the solar wind, it is not merely leaving a chemical residue, it is generating an electromagnetic trail. This trail propagates at the speed of light and possesses the capacity to influence regions far beyond where the physical material ultimately lands. Mars happens to be situated within the path of this trail. While not in a perfectly linear alignment, the comet's close approach trajectory did not place Mars directly behind the 3 Atlas. It was sufficiently close for the outer edges of the tail to potentially sweep past or through the planet. Although Mars lacks a global magnetic field, it possesses an induced magnetosphere. This is a bubble-like region formed by the solar wind exerting pressure on the upper atmosphere. This bubble can capture plasma and channel it, directing it towards the atmosphere or the surface. There are precedents for such interactions. Coronal mass ejections from the Sun, which involve bursts of plasma and magnetic fields, regularly impact Mars. During these events, the Martian magnetosphere is compressed, and charged particles are funneled down along the field lines of crustal magnetic anomalies. These particles can reach the surface, affecting atmospheric chemistry, generating nitrogen oxides, breaking apart molecules, and depositing energy. If a coronal mass ejection can exert such an influence, then a comet's plasma tail, while less energetic, can still interact with Mars in subtle ways. Now, let us consider the composition of that plasma. It contains ions of water, H+, O+, ions of carbon dioxide, CO2+, C+, ions of cyanide, Cn+, and ions of nickel, Ni+. These are not neutral atoms, they are charged, reactive entities. When charged particles interact with a surface, when they strike dust grains, ice particles, or rock, they do not simply rebound, they adhere, transfer energy, and drive chemical reactions. This process is known as ion implantation in material science. It involves directing a beam of ions at a surface. The ions penetrate a few nanometers, embedding themselves within the material and altering its surface properties, creating defects and introducing dopants. This technique is employed in semiconductor manufacturing, metal hardening, and the modification of optical coatings, and it occurs naturally when plasma interacts with solid matter in space. Cosmic ray particles affect asteroids in this manner, and the solar wind influences the Moon. Similarly, a comet's plasma tail could impact Mars. The key difference lies in its composition. Cosmic rays primarily consist of protons and helium nuclei, which are relatively simple. The solar wind is composed mainly of hydrogen and helium, with trace amounts of heavier elements. However, the plasma tail of the 3 Atlas carries nickel and cyanide, complex ions and molecules. When these ions strike Martian dust, embedding themselves at the molecular level, they are not merely contaminating the surface. They are doping it, priming it, and creating sites where chemical reactions can occur more readily. To be specific, imagine a dust grain, predominantly composed of silicon and perhaps some iron oxides. If it is impacted by a beam of nickel ions, some of these ions will adhere to the surface, forming nickel-rich areas. Subsequently, if this grain is exposed to water vapor, either from sublimating ice or the sparse atmospheric humidity on Mars, a reaction can be initiated. Water molecules adhere to nickel sites preferentially. Nickel possesses a hydrophilic nature, drawing water to it. Where water congregates, other substances follow suit. These can include organic compounds, salts, or any other materials present. The nickel then functions as a nucleation point, akin to a seed crystal, providing a foundation for complexity to begin organizing itself. Now, imagine this process occurring across millions of dust grains dispersed over vast expanses of the Martian surface. The plasma emanating from the comet 3I Atlas, as it made its pass, deposits nickel ions, thereby creating a surface dotted with numerous nucleation sites. Consequently, when robotic probes arrive to process the Martian soil, they are not merely extracting water from ordinary dirt. Instead, they are retrieving water from soil that has been chemically altered, activated, and rendered more reactive by the influx of material originating from an interstellar visitor. A contributor on X remarked that Mars presents a straightforward scenario: dust, vapor, and molecules settling from the comet's coma onto the surface. However, the process of information transfer is far more subtle. Information need not be encoded in a written language or in binary form. It can manifest structurally and organizationally, evident in the arrangement of molecules, the flow of energy through a system, and the patterns that emerge from the interaction of numerous components. Plasma itself carries information within its structure through density waves, magnetic field configurations, and oscillations in electric potential. These are not random occurrences. They are shaped by the conditions at their source, including the rate of outgassing, the composition of the coma, and the interaction with the solar wind. As this plasma propagates through space, it can influence other systems, induce electrical currents, cause perturbations, and trigger instabilities that would not otherwise arise. Consider the principle behind radio waves. Information is not transmitted by hurling particles, but by modulating an electromagnetic field to create patterns within the wave. These patterns convey the signal, and any device equipped with an antenna capable of detecting field variations can decode the message. While plasma does not transmit radio waves, it does generate low-frequency electromagnetic oscillations such as Alfvén waves and Langmuir waves. These waves propagate through the plasma, carrying energy and momentum, and possess the capability to interact with other plasmas they encounter, like the Martian ionosphere. Is 3i Atlas intentionally broadcasting? Almost certainly not in the conventional sense. However, is it generating patterns within the plasma that could, in principle, carry structure and influence the electromagnetic environment around Mars in ways dictated by the comet's composition and outgassing history? Yes, that is simply a matter of physics. The critical question is whether these patterns hold significance, whether they are substantial enough to affect anything. Is the plasma structure merely noise, or is it sufficiently coherent to be considered information? We lack direct measurements of this. No spacecraft was positioned to sample the plasma between 3 Atlas and Mars during its close approach. We possess models and simulations that predict cometary plasma tail behavior based on solar wind conditions and cometary activity levels. However, models are not empirical data. They are based on assumptions. For an object as anomalous as 3i Atlas, with its peculiar chemistry and unusual trajectory, these assumptions may not hold true. What we do understand is that Mars's crustal magnetic fields create conduits. The southern highlands exhibit strong localized fields, representing ancient magnetization imprinted in the rocks. These fields channel charged particles, directing them towards the surface. Furthermore, the southern highlands represent the oldest and most stable terrain, with deposits dating back to the Noachian period, approximately 4 billion years ago. If one were to seed a planet, to deliver materials to regions where they could persist and accumulate over geological timescales, the prime targets would be the most ancient surfaces, areas with minimal erosion where chemical processes could unfold slowly. The plasma tail from 3i Atlas could have achieved this targeting naturally, not through deliberate aim, but because the magnetic geometry inherently favored it. There is an additional factor to consider. Plasma possesses memory, not a conscious recollection, but a physical one. Once a gas is ionized to form plasma, it does not instantly forget its history when conditions shift. Electric fields generate currents, which in turn produce magnetic fields. Magnetic fields can then confine plasma, leading to further current generation. This establishes a feedback loop, a self-sustaining structure. On Earth, we observe this in the magnetosphere, plasma sheets, and radiation belts, where charged particles remain trapped for days or weeks, circulating and interacting. While Mars lacks the same extensive magnetosphere, it does exhibit transient plasma structures. These are plasma clouds that form when the solar wind compresses the ionosphere. These clouds can persist for hours and drift across the planet. If the plasma from 3I Atlas mingled with these clouds during the close approach on October 3rd, injecting nickel and cyanide ions into the Martian plasma environment, those ions could have circulated, dispersed, and eventually precipitated onto the surface in areas far removed from the comet's direct path. This would result not in a localized deposition, but a distributed one, covering a wider area and ceding more ground. This is speculative, but it is grounded in our understanding of plasma physics. The underlying mechanisms are understood, and the behaviors are predictable. What remains unpredictable is the significance of these events. Whether the trace amounts of nickel and organic compounds delivered via plasma will have any discernible impact, whether they are sufficient to alter the chemistry in detectable ways, whether they create conditions that would not have otherwise existed, and whether those conditions matter when the robots begin their excavation. The answer likely hinges on scale. A few scattered ions across the planet are unlikely to be significant. However, if the plasma tail was sufficiently dense, the outgassing rate high enough, and the interaction with Mars prolonged, the deposition could be substantial, priming entire regions and creating a landscape subtly yet meaningfully altered from its prior state. By July of 2025, we will not know the extent of this influence until we excavate, analyze Martian soil samples from multiple locations, and compare their composition to expected values, looking for anomalies, signatures, or traces of the visitor that passed by and left something behind. The anti-tail and other anomalies. On July 21, 2025, the Hubble Space Telescope focused on 3 Atlas and captured an image of something unexpected, a tail pointing towards the sun, not away from it. This suggested the comet was defying a fundamental principle of cometary physics. Cometary tails invariably point away from the sun due to solar radiation pressure pushing dust particles outward and the solar wind sweeping ions away. Both forces act radially from the sun, causing both the dust tail and the ion tail to trail behind the comet. Tails pointing sunward are not observed, as no force pushes in that direction, except it seemed in the case of 3 Atlas. The Hubble image revealed a teardrop-shaped coma, bright and diffuse, with a faint extension reaching back towards the sun. While not a prominent tail visible to the naked eye, it was discernible in processed images, sufficiently so for the analyzing team to offer an explanation: an anti-tail. The term, while sounding like science fiction, refers to a documented phenomenon in a few rare cometary observations. An anti-tail isn't truly pointing towards the sun. It's an optical illusion caused by a projection effect. Here's how it works. Comets continuously shed particles, including dust grains. Solar radiation pressure nudges these grains into orbits slightly divergent from the comet's own. While most of these grains are propelled outward, away from the sun, forming the typical dust tail, some larger, heavier grains lag behind. These heavier particles spread out along the comet's orbital path, forming a thin sheet of material within the orbital plane. When Earth, or in this instance a space telescope, observes the comet edge-on, nearly in the plane of this dust sheet, the sheet appears projected as a line. Depending on the viewing geometry, this line can seem to extend towards the sun. It's not physically directed sunward, but rather aligned with the orbit. However, from our vantage point, the projection creates the appearance of a sunward spike, an anti-tail. This phenomenon has been observed before in comets like Comet Schwarzmann-Wachmann 1 in 1957 and Comet Hale-Bopp in 1997. Its rarity stems from the precise geometric alignment required, but it is not unprecedented. Therefore, the Hubble observation of an anti-tail around 3I Atlas is explainable. It is unusual, certainly, but not impossible, not a violation of physics, merely a peculiarity of viewing angle. However, the anti-tail was not the sole anomaly captured by Hubble. The image also showed something else, or rather, failed to show something it should have: a dust tail. Comets at 3 Atlases distance from the Sun, approximately 3.8 astronomical units during the Hubble observation, are expected to possess visible dust tails. The sublimation of ice releases dust particles, which are then pushed away by radiation pressure. Over days and weeks, these particles spread out to form a luminous arc stretching millions of kilometers. This is the typical appearance of a normal comet, and it is what Hubble was looking for. Yet, 3I Atlas lacked one. The image displayed the coma and the anti-tail, but the anticipated bright dust tail was conspicuously absent. The analyzing team noted this in their report, suggesting possibilities such as low dust production or a comet composed primarily of volatile ice with minimal dust contamination. Alternatively, they posited that the dust grains might have been large and dark, reflecting insufficient sunlight to render the tail detectable. While these explanations are plausible, they are unsatisfying, especially considering that later ground-based telescope observations in August and September did reveal a tail, albeit faint, which indicates that dust was indeed present and the comet was shedding particles. So, why was the tail not visible to Hubble in July? Why was it either missing or suppressed in early observations, only becoming apparent later? One potential explanation is variability in activity. Comets do not outgas uniformly. They exhibit jets, regions on the nucleus that are more active than others. As the nucleus rotates, different areas are exposed to the Sun, leading to fluctuations in the outgassing rate. It is possible that in July the active regions were oriented in such a way that dust production was minimal, and by August, the comet's rotation brought more active areas into sunlight, increasing dust output. This timeline could be reconciled. However, it does not account for the anti-tail, which necessitates dust present along the orbital path. Dust shed over an extended period and spread into a sheet. If the comet was producing very little dust in July, then where did the material forming the anti-tail originate? It must have been released earlier, weeks or even months prior to Hubble's observation, when the comet was farther from the Sun, colder, and less active. This suggests that 3 Atlas was shedding material significantly earlier than expected for substantial outgassing, which is another anomaly. Comets typically do not become active until they are within approximately 4 astronomical units of the Sun. 3E Atlas, however, showed activity at 6 astronomical units, and perhaps even earlier. Then there is the matter of color change. In early September, amateur astronomers in Austria captured images of 3 Atlas emitting a green glow. Comets appear green when they produce diatomic carbon molecules, C2, which fluoresce at a specific wavelength when exposed to sunlight. This is a common observation, with most bright comets exhibiting some green coloration. The underlying process is well understood. Organic molecules within the nucleus, specifically long-chain hydrocarbons, break down under sunlight. These fragments include C2, which emits green light before further disintegrating into individual carbon atoms. However, spectroscopic analysis conducted using the Very Large Telescope indicated that 3I Atlas was depleted in diatomic carbon. Its coma was predominantly composed of carbon dioxide and carbon monoxide, CO2 and CO, not the long-chain organic materials required to produce C2. Therefore, the comet should not have appeared green, yet the images clearly showed green emission. The most probable explanation, as previously discussed, is the presence of cyanide, CN. Cyanide molecules fluoresce at wavelengths close to those of C2, and 3I Atlas is producing cyanide in significant quantities. Thus, the green coloration is likely attributable to CN, not C2. The mystery appears solved. Yet this raises another question. If the comet is dominated by CO2 and contains minimal complex organic material, where is the cyanide originating from? Hydrogen cyanide, HCN, is a simple molecule, requiring hydrogen, carbon, and nitrogen. Hydrogen is present in the form of water, and carbon is present in CO2. However, nitrogen is less abundant. The Martian atmosphere is primarily CO2, with a small percentage of nitrogen. Comets typically contain nitrogen in the form of ammonia or molecular nitrogen, but these are volatile and sublimate at very low temperatures. By the time a comet reaches 3 astronomical units, close enough for easy observation, most of its nitrogen should have dissipated. Yet, 3E Atlas continues to produce increasing amounts of cyanide as it approaches the Sun, as if it has a deep, untapped reservoir of nitrogen. This observation is linked to another anomaly, the water production rate. At 3.5 astronomical units, most comets exhibit minimal water outgassing. Water ice efficiently sublimes only when the surface temperature exceeds approximately 200 Kelvin. At 3 Atlas's distance in late July, the solar flux was low and the expected sublimation rate was minimal. Nevertheless, the Swift Observatory detected significant water emission at a rate of 40 kilograms per second. This is a substantial amount, indicative of an active comet, comparable to outgassing rates expected at 2 astronomical units, not 3.5. Explanations offered in scientific papers suggest that 3 Atlas might possess a high albedo, meaning a bright surface that absorbs less heat, or a fluffy, porous structure that allows heat to penetrate deeper, sublimating ice beneath the surface. Alternatively, the water could be originating not directly from the nucleus, but from ice grains ejected into the coma that subsequently sublimate in sunlight. While all these possibilities are plausible and could explain high water production at large distances, none adequately account for the steepness of the production curve, the exponential ramp as the comet approaches the Sun, a power law with an exponent of -9. Such a pronounced dependence suggests a process beyond simple thermal sublimation, hinting at an energy-intensive reaction. This could be a process that requires an initial energy input to overcome a barrier, but then proceeds rapidly once initiated, akin to combustion or a chemical reaction with a high activation energy. The reaction needs sufficient energy to surmount the barrier, but once it does, it proceeds quickly. What chemical reaction could exhibit such a steep temperature dependence on a comet? One possibility is that the comet's composition is not purely ice. It may consist of a matrix of ice, organic compounds, and potentially other substances. As the surface heats up, the matrix undergoes phase changes. Ice melts or sublimates, organic compounds decompose, and trapped volatiles are released. This initiates a chemical cascade, where one step triggers the next. The overall effect is a release rate that increases exponentially with temperature. This is speculative, but it aligns with the observations and suggests that 3 Atlas is not a simple, dirty snowball, but a complex chemical system that activates in stages as it heats up. Amateur astronomers have added another layer to the enigma. Stefan Burns, observing from Germany, posted a time-lapse animation of 3 Atlas in early October. Other observers analyzed these frames and claimed to identify multiple objects, not just the comet nucleus, but additional points of light moving in close proximity, distinct entities, potentially co-traveling objects. These included C2025 A6 Lemon, C2025 R2 Swan, and C2025 K18 Atlas, all identified as separate comets, but appearing within the same field of view as 3I Atlas. This is where the situation becomes less clear. Were these genuinely separate comets traveling together, or were they fragments that had detached from 3I Atlas? Or perhaps they were misidentified. Could this be part of a stream of material ejected from a distant system? Or did it break apart during its journey, shedding pieces that are now trailing it through the solar system? Comet fragmentation is a common occurrence. Thermal stress can fracture the nucleus, and outgassing can create jets that spin the nucleus to the point of disintegration. We have witnessed this phenomenon numerous times. Comet Shoemaker-Levy 9 fragmented into more than 20 pieces before impacting Jupiter. Comet Schwarzmann-Wachmann 3 split into dozens of fragments that dispersed along its orbit. If 3I Atlas is fragmenting, shedding pieces as it approaches perihelion, this could account for some of its anomalous behavior. Multiple active regions, varying outgassing rates, and unpredictable dust production, with each fragment contributing to the overall coma, but with slightly different characteristics. However, fragmentation also raises questions about targeting. If the comet is breaking apart, with pieces separating and following slightly different trajectories, then the precision of the Mars close approach becomes even more remarkable, as one would need to account not only for the main nucleus, but also for its fragments. Furthermore, if these fragments are also carrying a payload and releasing nickel and cyanide, the delivery would become distributed, resulting in multiple impact points or deposition zones, leading to a broader seeding pattern rather than a concentrated one. The observations from Mars orbiters during the October 3rd close approach have not yet been fully released. We know that the ExoMars Trace Gas Orbiter captured images and that Mars Express gathered spectroscopic data, but the detailed analysis and breakdown of what was actually observed remain confidential. NASA mentioned that the high-resolution imaging science experiment, HiRISE, camera on the Mars Reconnaissance Orbiter would image 3I Atlas at a resolution of 30 kilometers per pixel. This resolution is sufficient to distinguish the nucleus from the coma and to observe structure, potentially even detecting fragments if they exist and are large enough. The fact that this data has not yet been released is noteworthy in itself, though not necessarily indicative of suspicion. Scientific data requires time for processing, analysis, and preparation for publication. However, for an event as anticipated as the flyby of an interstellar comet past Mars, one would expect prompt preliminary results, a press release, and some images to satisfy public curiosity. The prolonged silence suggests either that the observations were inconclusive, too faint or ambiguous to be useful, or that they revealed something requiring careful interpretation, something unexpected. Let us consider one more anomaly: polarization. A team utilizing the Very Large Telescope measured the polarization of light reflected by 3I Atlas. Polarization provides information about the size and composition of particles within the coma. Dust grains scatter light differently depending on their shape, size, and material. By measuring the degree of polarization of the scattered light, one can infer properties of the dust. The results were unprecedented. 3I Atlas exhibited a negative polarization, minimum of -2.7%, at a phase angle of 7 degrees. The inversion angle, the point at which polarization shifts from negative to positive, was approximately 17 degrees. These figures are unusual, though not impossible. The polarization behavior of 3 Atlas does not align with any known comet or asteroid within our solar system. It is an outlier. Again, negative polarization at small phase angles is characteristic of very dark or fluffy surfaces, materials with complex porous structures that scatter light in specific ways. However, the magnitude of the negative polarization for 3I Atlas is stronger than anticipated, and the narrow inversion angle suggests particles with unusual optical properties. This could imply that the dust grains are composed of materials not commonly found in comets, or that their structure is atypical, perhaps comprising aggregates, fractal clumps, or something that deviates from standard models. This finding connects back to the missing dust tail. If the dust particles are large, dark, and possess unusual structures, they would reflect very little sunlight, resulting in a faint tail that would be difficult to detect, which is consistent with what Hubble observed in July. However, this does not account for the later increased visibility of the tail, that is, unless the dust characteristics underwent a transformation. Perhaps early outgassing yielded one kind of particle, and subsequent venting produced a different type. This scenario would necessitate variations in the nucleus's composition, implying stratification and heterogeneity rather than uniformity. Different substances would reside at distinct depths. Such layering is not uncommon. Many comets exhibit it, with dark, processed material on the surface overlaying fresher ice beneath. As the comet warms and its surface erodes, new material is exposed, altering the outgassing. Yet, for Three-Eyed Atlas, the time frame is compressed, with changes occurring over weeks instead of months. This suggests either extremely thin surface layers or exceptionally rapid heating. Both are plausible, but they add to the list of factors making this comet distinctive. Therefore, our current understanding is as follows: an anti-tail indicative of early dust production, a previously absent dust tail that subsequently appeared, a green hue attributed to cyanide despite depleted dicarbon, exponential water and cyanide outgassing highly dependent on temperature, potential fragmentation or co-traveling entities, anomalous polarization suggesting unusual dust properties, and all of this from an interstellar traveler making a precisely timed close pass by Mars 2 years before robotic landings. Each anomaly possesses a potential natural explanation, such as viewing geometry, compositional variation, peculiar thermal characteristics, or optical effects. Nevertheless, when these anomalies are considered collectively, their cumulative impact becomes substantial. Not definitive proof, but rather an indication of extraordinary qualities. These peculiarities exhibit a pattern, seemingly orchestrated as if the comet were designed to be enigmatic, offering just enough natural explanations to preclude definitive artificial classification, yet not enough to be comfortably deemed entirely natural. Perhaps this is the intended outcome. Maybe these anomalies are not accidental but rather deliberate features. They could be mechanisms to ensure the object receives thorough investigation, garner significant attention, and be taken seriously by the scientific community. If Three-Eyed Atlas were unequivocally artificial, perhaps broadcasting radio signals or displaying geometric structures, our response would differ. We would mobilize, dispatch missions, and investigate with utmost urgency, but also with caution and apprehension. Conversely, ambiguity, a level of strangeness that sparks curiosity without posing a threat, elicits a different engagement. We would study it scientifically, engage in debate, and dispatch robotic probes to its prior locations, not in pursuit of extraterrestrials, but as a consequence of scientific inquiry. In doing so, we would achieve precisely what a seeding operation might desire. We would delve, process, and activate the underlying chemistry. The question of its age, an age predating our sun. A specific figure, 7 billion years, frequently appears in scientific papers concerning Three-Eyed Atlas. This is an estimation derived from velocity and trajectory modeling. However, if even remotely accurate, it implies that Three-Eyed Atlas is over 2 billion years older than our entire solar system. It predates the Sun, Earth, and everything in our immediate cosmic vicinity. This profound age fundamentally alters the context of our discussion. Our solar system originated approximately 4.6 billion years ago. This is established through radiometric dating of meteorites, with the oldest terrestrial, lunar, and Martian rocks dating to around that period, specifically between 4.5 and 4.6 billion years. This timeline is consistent. A nebula of gas and dust collapsed under its own gravity, forming the Sun at its center and flattening into a disk from which planets coalesced over a few million years. By 4.5 billion years ago, the fundamental structure was in place with Earth, Mars, Jupiter, and others orbiting. However, 7 billion years ago, the universe was different. Galaxies were younger, having undergone fewer stellar life cycles and supernova enrichments. The metallicity, the abundance of elements heavier than hydrogen and helium, was generally lower. While the universe was already 9 billion years old enough for multiple stellar generations, the prevalent material composition favored lighter elements, resulting in less carbon, less oxygen, and less iron, with potentially different elemental ratios in certain regions. The modeling suggesting this immense age stems from an analysis of 3I Atlas's velocity relative to the local standard of rest, LSR. The LSR represents the average motion of stars in our galactic neighborhood. Most nearby stars orbit the galactic center at a speed comparable to ours, roughly 220 kilometers per second. Their relative motions are minor, on the order of tens of kilometers per second. However, 3I Atlas deviates from this local flow. Its velocity vector, after accounting for the sun's motion, points in a specific direction with a magnitude suggesting an origin from the galaxy's thick disk. The Milky Way comprises distinct structures: a thin disk where most stars reside, a thicker disk of older stars situated above and below the thin disk, a halo of very ancient stars forming a roughly spherical distribution, and a central bulge. Each stellar population possesses unique ages and metallicities. The thin disk contains young, metal-rich stars like our Sun, whereas the thick disk is composed of older, metal-poor stars that formed when the galaxy was younger. If 3I Atlas originated from the thick disk and its trajectory traces back to this population, then it likely formed around a star within that population. Such stars are ancient, ranging from 7 to 10 billion years old. This conclusion is not definitive. Velocity alone cannot precisely determine age. However, it is suggestive and aligns with other observations. The elevated ratio of carbon dioxide to water is another unusual characteristic for comets within our solar system, which are typically water-rich. In an environment with lower metallicity and less abundant oxygen, a higher proportion of carbon monoxide and carbon dioxide relative to water might be expected, leading to different chemical equilibrium conditions. The ices that condense in a protoplanetary disk around a metal-poor star could possess compositions not observed locally. 7 billion years is an extensive period, sufficient for civilizations to emerge and decline. It is long enough for a planet to complete its habitable phase, develop life, evolve intelligence, construct technology, and subsequently confront whatever existential challenges advanced civilizations face. The Drake equation, which estimates the number of communicative civilizations in our galaxy, includes a factor for the longevity of civilizations, the duration of their broadcasting or existence. This value remains unknown. It could be 100 years, 1 million, or even longer. However, 7 billion years allows for numerous cycles and attempts. If 3I Atlas originated from a system of that age, perhaps constructed, launched, or seeded by intelligence from that era, then we are not dealing with contemporary aliens, but ancient ones, beings or machines that may no longer exist. The light from their star would take thousands of years to reach us, and any signal they transmitted would be similarly ancient. Furthermore, if they launched 3I Atlas on an interstellar journey, the travel time alone could span millions of years. At speeds of tens of kilometers per second, relative to local stars, traversing hundreds or thousands of light years would take eons. This aligns with the Bracewell probe hypothesis, the concept that instead of broadcasting radio signals which attenuate with distance, advanced civilizations might dispatch physical probes, possibly self-replicating machines, to explore other star systems, gather information, and potentially relay findings or execute long-term missions. The advantage of probes lies in their persistence. A radio signal is transient. Missing its reception window means it is lost. A probe, however, can linger, observe a system for centuries, and activate upon detecting significant developments, such as the emergence of a technological civilization. If 3I Atlas is a Bracewell probe, its purpose is not communication. It has not transmitted radio signals, nor has it exhibited overt artificial structures. Its objective is to deliver, to seed, or to prepare Mars for a specific outcome. Its age is consistent with such a mission profile. One would not dispatch a probe on a million-year voyage if immediate results were required. Such a mission would be undertaken with a long-term perspective, playing a game spanning geological epochs rather than mere decades or centuries, employing a strategy of planting seeds across numerous systems and allowing time to facilitate their growth. Consider it from the viewpoint of a civilization existing 7 billion years ago. They might have mastered their local environment, perhaps their solar system or nearby stars. However, they would understand from physics that interstellar travel is arduous. Exceeding the speed of light is impossible, and achieving even a significant fraction of light speed demands immense energy. Transmitting living organisms presents further challenges, necessitating life support, radiation shielding, and mitigating the psychological effects of prolonged confinement. It would be more practical to send machines or raw chemical materials capable of self-assembly at their destination. From the perspective of such a civilization, operating on billion-year timescales, micromanagement would be unnecessary. They would establish initial conditions, send a payload to a young planetary system, deliver essential building blocks, water, carbon, nitrogen, catalytic metals, and then allow the local environment to facilitate assembly. In a lifeless system, the chemistry might remain dormant. However, if the system develops life, or if an external intelligent species arrives and begins manipulating the environment, the chemistry would activate, interact, and become integral to whatever emerges. This concept is known as directed panspermia, but in a chemical rather than biological form. Instead of transmitting bacteria or spores, it involves sending molecules and precursors that could evolve into life under appropriate conditions, but are not life themselves. This approach is less intrusive and potentially more resilient, as bacteria might not survive the journey due to cosmic rays, radiation, or the passage of time. However, chemicals encased in ice and protected by a rocky matrix can endure indefinitely, potentially for billions of years. The age of Three-Eyed Atlas also raises questions about navigation. If it was launched 7 billion years ago, or even 4 or 5 billion years ago, the galaxy would have presented a different configuration of stars. The Sun would not have existed yet. Therefore, how did the probe locate us and arrive at this specific juncture? The answer is that it likely did not target us precisely. However, it did not need to. If thousands or millions of probes were launched, each directed towards a different system, success would not depend on any single probe, but rather on probability. Most would miss their intended targets, passing through systems devoid of planets, with dead planets, or planets that never developed anything significant. However, a select few would achieve fortunate arrivals, reaching systems with potential and delivering their payloads at opportune moments. These rare successes would justify the entire undertaking. We might represent such a success. Earth and Mars are in the same system. One harbors established biology, while the other is barren yet accessible. Precisely as Earth's civilization achieves the capability to explore Mars, an interstellar visitor appears and seeds it. This is not targeted precision, but rather good fortune. However, it is luck on a galactic scale, where the deployment of so many probes makes fortunate outcomes statistically inevitable. Alternatively, it might not be mere chance. There could exist an unknown mechanism enabling the detection of technological activity across interstellar distances, not through radio signals, but via other means such as neutrinos, gravitational waves, or disturbances in the interstellar medium caused by spacecraft or energy production. If Three-Eye Atlas is a probe possessing some form of autonomous sensing capability, it might have detected us, perhaps our electromagnetic emissions. It could have then subtly adjusted its trajectory, with a minor velocity change of only a few meters per second over millions of years, enough to direct it towards the inner solar system rather than allowing it to pass through the outer reaches. Such adjustments are plausible with propulsion systems like solar sails or gravitational assists from stars encountered centuries prior, where small corrections accumulate over vast timescales. Even if 3I Atlas is entirely natural, an exceptionally old and chemically peculiar comet, its age remains significant. It provides insights into the diversity of galactic materials and how varied star-forming environments yield different ices, organics, and elemental ratios. If a single ancient comet can deliver such unusual chemistry to Mars, what about others? Those we have not yet detected, or those that traversed our solar system before our observational capabilities were established? How frequently has Earth received interstellar material? To what extent does our own chemistry and biology originate from extraterrestrial deliveries? Isotope ratio studies in Earth's oceans suggest a substantial portion of our water originated from comets, supplementing the water present at Earth's formation. Comets delivered volatiles during the late heavy bombardment approximately 4 billion years ago, a period of significant planetary system upheaval and frequent impacts. If some of these comets were interstellar, carrying not only water but also organics and metals from other star systems, then Earth's biology might represent a hybrid. It could be locally evolved yet influenced by foreign chemistry, not in the form of fully formed alien life, but through alien molecules contributing to the prebiotic environment. Three-eyed Atlas demonstrates the possibility that interstellar comets transport complex chemistry, deliver it to planets, and that the timing of such delivery can coincide, either by chance or design, with critical transitional phases, moments when a planet is on the cusp of something new. For Earth, this pivotal moment was approximately 4 billion years ago, marking the origin of life. For Mars, that moment is now, with the arrival of intelligence. Not biological intelligence yet, but technological intelligence embodied in machines capable of manipulating matter. And perhaps, given the right chemical conditions, these machines could evolve into something more. What will transpire next? The timeline. We are currently in a period of anticipation. From Earth's perspective, Three-Eyed Atlas passed behind the Sun in mid-October, rendering it unobservable for several weeks due to its proximity to solar glare. Ground-based telescopes could not track it, and space telescopes had to avoid pointing near the Sun. The comet became invisible, but not inactive. Its perihelion, the closest approach to the Sun, occurred on October 30th, at 1.4 astronomical units, situated just inside Mars' orbit. This is the point of maximum solar heating, peak outgassing, and the most intense solar radiation exposure during this passage. We do not know what transpired at perihelion. Whether the comet remained intact, fragmented, experienced further increased or decreased outgassing, or whether its anomalous behaviors intensified or resolved. All pertinent data is currently inaccessible, awaiting the comet's re-emergence on the opposite side of the Sun, which is anticipated in early December. By then, it will be moving away from the Sun, receding. The spectacle will be drawing to a close, but the post-perihelion observations will be crucial. This phase reveals the comet's composition and its response to maximum stress, indicating whether it is robust or fragile. If Three-Eyed Atlas is a natural object, an unusually old and chemically peculiar comet, perihelion might have caused its disintegration. The thermal stress, rapid heating, and outgassing pressure could fracture the nucleus. We have witnessed similar events with sun-grazing comets, which completely disintegrate upon approaching the Sun, leaving behind only a dispersing cloud of vapor and dust. Three-Eye Atlas was not a sun grazer. 1.4 AU is relatively safe. However, for a pristine interstellar object, one that has never previously experienced significant solar heating, Even this distance could induce breakup. Conversely, if Three-Eyed Atlas is artificial or partly artificial, perihelion might have been a deliberate event. Maximum heating and outgassing could represent the final stage of payload release before the object re-enters a dormant state, a calculated expulsion of material. In such a scenario, the December observations should depict a depleted comet, quieter and less active, having fulfilled its delivery objective. Spacecraft observations represent the next significant data release. The European Space Agency's JUICE mission is scheduled to observe Three-Eyed Atlas in November. Although JUICE is en route to Jupiter and will not arrive for several years, its trajectory in November will provide a favorable vantage point for observing the comet. The spacecraft is equipped with multiple instruments, including cameras, spectrometers, and particle detectors, enabling detailed measurement of coma composition, far exceeding the capabilities of ground-based telescopes. Furthermore, because JUICE will be observing the comet post-perihelion, when activity is expected to be high, the signal strength will be considerable. However, there is a complication. JUICE is currently distant from Earth, on the opposite side of the Sun, which limits communication capabilities and data transmission rates. The spacecraft is utilizing its high-gain antenna as a heat shield, directing it towards the Sun for protection. Consequently, communication must be established through a smaller, less capable antenna. While the observations will be conducted and the data collected, it will not be transmitted back to Earth until February 2026, necessitating a 3-month waiting period without knowledge of JUICE's findings. This delay, while frustrating for those following the event, is also strategic, allowing time for analysis prior to public disclosure and enabling the scientific community to prepare for any revelations. Should JUICE detect anything unusual or paradigm-shifting, the team will require absolute certainty before publication. They will conduct thorough checks, compare findings with models, and consult with other experts, a process that inherently requires time. Data from Mars orbiters, including the high-resolution imaging science experiment, HiRISE, on the Mars Reconnaissance Orbiter, and cameras on Mars Express and the ExoMars Trace Gas Orbiter are also relevant. These instruments were directed towards Three-Eyed Atlas during the close approach on October 3rd, capturing images and spectra. As of mid-October, none of this data has been publicly released. This could indicate several possibilities. The data is still undergoing processing, which involves image stacking, calibration, and analysis, a normal and expected procedure. Alternatively, the data might be ambiguous, too noisy, too faint, or otherwise unsuitable for drawing firm conclusions, which is plausible given the distances involved. A third possibility is that the data reveals something unexpected, requiring careful interpretation and context before public dissemination to avoid causing more confusion than clarity. This scenario fuels ongoing speculation, suggesting that the spacecraft observed something intriguing, perhaps not definitively conclusive, but sufficiently noteworthy to warrant extended analysis before its release. We will not know for certain until the data is released. When it is, it will likely appear in scientific papers, characterized by peer-reviewed publications, dry language, cautious disclaimers, and a lack of bold assertions, presenting only observations and interpretations accompanied by error margins and caveats. This is the standard scientific methodology. However, even understated papers can contain revelations, numerical discrepancies, unexpected elemental compositions, or images depicting structures where none should exist. The details are paramount, and for an object as anomalous as Three-Eyed Atlas, these details will undergo intense scrutiny. Beyond the immediate observations, there is the longer-term timeline involving robotic exploration. Elon Musk has stated a goal of late 2026 for the inaugural uncrewed Starship landing on Mars. This timeline is ambitious and potentially unrealistic. Starship is still undergoing testing, and while recent flights have been successful, transitioning from successful tests to an operational Mars mission involves numerous complex stages, including life support, navigation, landing systems, and payload integration, all of which must function flawlessly. Furthermore, space missions are prone to delays caused by technical issues, funding constraints, and regulatory obstacles. Even should the projected launch dates be delayed and the initial robotic explorers not reach the Martian surface until 2027 or 2028, their arrival is inevitable. The necessary infrastructure is currently under construction, and the operational blueprints are continuously being refined. Upon their deployment, a primary function of these sophisticated machines will be the extraction of planetary resources. This will involve excavating Martian regolith, processing it to extract water, and conducting detailed analyses to identify valuable mineral deposits. Crucially, as they perform these operations, they will inevitably collect samples from the very strata where the payload of the 3i Atlas spacecraft previously deposited its contents. It is entirely plausible that these robots will not be aware of the specific nature of the materials they are sampling. The mission architects are not presently considering the implications of interstellar comets when formulating excavation protocols, but the chemical signatures will undoubtedly be present and awaiting detection. The robots are programmed to analyze all materials they encounter, as a fundamental part of their mission involves understanding Martian geology and assessing the availability of resources. The gathered data will be transmitted back to Earth for examination by scientists. Should any anomalies arise, for instance, if nickel concentrations exceed anticipated levels, or if organic compounds are discovered in locations where their presence is scientifically improbable, these discrepancies will be noted. Questions will be raised, and eventually, a connection will be made. Ah, this is the location where the 3i Atlas passed. This is where its plasma trail might have intersected with the Martian surface. This is where the coma of the comet swept over the planet. Could there be a link? At this juncture, the narrative transitions. The hypothetical scenario evolves into a formal scientific inquiry, transcending the realm of speculative theories disseminated on social media platforms. It transforms into a testable hypothesis, supported by empirical data. Subsequent observations would be designed, specific sites would be targeted for sampling, and compositions would be compared across various regions to identify gradients or signatures consistent with the comet's output. If such evidence is found, and it is confirmed that Martian soil has indeed been measurably influenced by the passage of the 3i Atlas, then an explanation will be required. This will necessitate the development of models to account for the delivery mechanism, the rates of deposition, and the chemical integration processes. Through this modeling, it may become apparent that the effects are substantial and that the chemistry involved is not merely trace contamination, but significant enough to warrant consideration. If these effects are indeed significant, and if they alter our understanding of Mars's potential to harbor complex chemistry, then the mission's priorities will necessarily shift. The focus will expand beyond simple resource extraction to include the study of prebiotic chemistry occurring on another planet, chemistry that has been recently enriched by an extraterrestrial source. Future missions would then be equipped with more advanced instrumentation, such as mass spectrometers, chromatographs, and microscopes. Samples would be subjected to culturing and reaction experiments to observe their behavior when exposed to heat, water, or energy. Investigations would explore whether nickel acts as a catalyst, if cyanide contributes to organic synthesis, or if their combined presence yields unexpected results. This is the trajectory we are currently on. December 2025 marks the commencement of renewed ground-based observations of the 3i Atlas as it reappears from behind the Sun. February 2026 is scheduled for the release of data from the JUICE mission. In late 2026 or early 2027, The first Optimus robots are slated to land on Mars and commence excavation operations. Between 2028 and 2030, the accumulating data from these robotic missions is expected to reveal compositional anomalies. From 2030 to 2035, targeted investigations are anticipated to confirm an interstellar contribution to Martian surface chemistry. Beyond this point, the timeline becomes increasingly speculative, contingent upon the actual consequences of this planetary seeding. If the deposited chemicals are inert, remaining in the soil without undergoing further reactions, scientific interest will be high, but practical implications will be limited. Mars would possess foreign molecules, a fascinating prospect for astrobiology, but not a paradigm-shifting development. However, if the materials are catalytic, with nickel and organic compounds accelerating specific reactions, thereby enhancing resource extraction efficiency or facilitating chemical synthesis, the practical ramifications would be considerable. Mars would become a more attractive destination for colonization, its environment rendered more amenable by the imparted chemistry. But if the chemistry exhibits self-organizing properties, beginning to build complexity independently, then the implications would be profound. We would be studying not just inert molecules, but the nascent stages of processes that could potentially lead to the emergence of life, or interact with living or technological systems in ways currently beyond our comprehension. It is at this stage that ethical considerations would arise. Would we intervene? Would we permit development to proceed naturally? Should we foster or suppress it? Do we possess the moral authority to make such decisions? These are questions for the distant future, potentially years or even decades away, but they are on the horizon. They originate from a critical decision point unfolding now, in December 2025, when we obtain our next comprehensive view of the 3I Atlas. This observation will reveal whether it has survived its perihelion passage, allowing us to measure its post-perihelion activity and compare it to pre-perihelion data. This comparison, while perhaps not offering definitive answers or settling all debates, will provide valuable insights. In the interim, while the comet is obscured by the sun, data is being processed and robots are being prepared. Chemical processes are already underway on Mars within the regolith. Nickel atoms are embedded in dust grains, cyanide molecules are frozen in ice, and water is locked within the permafrost. All of these elements are quiescent, awaiting a period of just 2 years, not eons, not geological timescales, but merely 2 years, until mechanical explorers arrive and commence excavation. Until artificial intelligence confronts emergent intelligence. Until the hybrid era begins. This is not mere conjecture about a distant future. It is the timeline we are presently navigating. The clock is ticking. The countdown has commenced. Regardless of whether the 3I Atlas was a natural phenomenon or an engineered entity, and whether its seeding of Mars was accidental or deliberate, the outcome remains the same. Mars has been prepared, the conditions are set, and we are on the verge of activating them,